City. Yes, my area lies in low dimensional topology and not theory and applications, so I will try to give you as much as possible a flavor of this area. So I will start from the basics because the audience is very diverse. A node, we call a node, a smooth embedding of the unit interval in the 3 space, R3 or in the 3 sphere, so that the ends meet. So it is a closed loop, let's say, in the 3 space, and the link with K components is a smooth embedding of K circles in the 3 space. And here we see, I think, the first notch up to 9 crossings, and some links of components here. This is the famous Hopf link, and so on. This is the trivial, the trefoil, the figure eight, pentafoil, and so on. So the open problem, which is still open in this area, is to classify all knots and links up to isotopy. Isotopy is the equivalence relation that is like an elastic, continuous elastic deformation of the ambient space that moves one knot onto the other. So this is our equivalence relation, which is much, of course, much more refined than homeomorphism, because all knots are homeomorphic to the trivial knot, so there is no distinguishing there. But isotopy really distinguishes the details of the knots and the complexity. So first to deal with knots, let's say, is Gauss, who in his study of the theory of electrodynamics, he drew in some handwritten notes, he copied some notes from the Journal of the Navy Academy of United Kingdom. And then, listing a student of Gauss, got interested in the theory as a mathematical theory, he started working on tabulating knots. Then we have Lord Kelvin, who made his theory on vortex atoms, where he claimed that, he made the theory that atoms are knotted tubes inside the ether. So he thought that if we classify these knotted tubes, that means the knots, then we classify the atoms in nature. So his collaborator, Peter Tite, started working for 20 years, trying to catalog knots up to 10 crossings. And this was really a long task, a difficult task, and it was soon the theory of Kelvin fell apart, because there are finitely many atoms in nature, but infinitely many and very difficult to classify knots, types of knots. Yet, the subject of knot theory was launched this way. Then, how to study knots, how to start thinking of classifying. Of course, we cannot think of yarns in space, lying and making elastic deformations. We project them on the plane, and then we try to study them through the projections. Here we see the projection of the Borromean rings. Borromei was a famous Italian aristocratic family in the lakes of Milano, and that was the family emblem. This is a for us it is a three-component link, and it has the property that if you remove any of these, the other two fell apart. So, therefore, we study the projections of knots, but we want special projections, which we call diagrams. Diagram means that we project on a specific plane, on any plane, the knot, so that we don't like pathologies like this, like three different arcs to project on the same point. We don't like these triple points and more. We like only double points. And we can avoid, because with a very small perturbation in space, we can avoid the triple points. So it's easy to dismiss such pathologies. Also the tangencies here. They are not, of course the arcs are not tangent in the space, but they project to tangency, and we don't like that either. Also the cusps, we don't like the cusps. But these pathologies, they all have measure 0 in the set of projections, so we can dismiss them. And we have the theorem of Kurt-Reidemeister, who translates the continuous deformation in space, what we call isotopy, the equivalence of knots in space, which is continuous, to combinatorial equivalence in the plane and with only finitely many moves. So Reidemeister discretized the notion of isotopy. So he says that two knots are isotopic. When we say knots, we mean knots or links. Are isotopic if and only if any two diagrams, any two projections in any planes, but appropriate projection. Diagram is only, as I said, diagram is only dismissing such things. So only double points in the projection, no tangencies, no cusps. So Reidemeister says that what we notice as we observe as pathologists, these are enough to generate isotopic equivalently in bijection. Therefore, knots are isotopic in space if and only if diagrams are related through this finite sequence of moves like that, which is totally discrete. I stress this point because then we have another revolution that it is becoming, the study could become also algebraic through the braid group. So, then in order to classify knots, okay, we start doodling, we make a doodle of the plane, and what Ty did, okay, the collaborator of Lord Kelvin, so we make a doodle, and then at every crossing, double point, we have to decide, is it over or under? Because for the diagram, we need to give this information for everything. So we have, for n crossings, double points, we have 2 to the n choices, and given any of these choices, we have to decide if this can be made simpler. Therefore, it is equivalent to something that we have already on the list, or if it cannot be simpler, so then it is a new thing on the list. So you see how complicated this is. Really, it has non-polynomial complexity, and as we said, up to 10 crossings, it was the work of Ty. That took him 20 years. Then we have some knot invariants that came along, like the Alexander polynomial, which help, and I will tell you immediately what I mean, and then things start, the revolution starts in our area in 1984 when von Jones discovered the famous Jones polynomial for knots. I will go a little faster here. So, we want to study questions, the simple questions to ask is why is the trefoil not equivalent to the trivial knot? But it is clear, but then we want to find a proof for that. A proof is through, for example, the first proof was through the complement. We take the knot complement in the 3 space and we show that the complements are not homeomorphic, for example. This is a method. Why the Hopf link is not isotopic to the trivial link? Why the right-handed trefoil is not isotopic to the left-handed trefoil. So, okay, so how do we distinguish knots and links? We construct functions because, you know, these are simple images, representations, but we could have something really complicated in space, very complicated, and it is very difficult to tell if it is trivial or not trivial, or if it is something we already have on the list or we don't have it. So, for this reason, we construct invariants, which are functions from the set of all knots, and we mean knots and links, we mean types of knots and links, that means equivalence classes, to some set of labels, polynomials, integers, and so on, or just labels on, off, yes, no, for example, 3 colorability. And it is invariant if, for equivalent knots, it gives the same value. Now, this means that if a particular invariant for 2 knots gives different values, then these are distinct knots. If it gives the same value, we cannot decide, because if we could decide if we could have a complete invariant, which we don't have because the problem is still open. Yet, given 2 complicated knots, okay, we want to decide if they are distinct or not. We apply on those 2 an invariant. If it gives the same values, we cannot decide, so we take another invariant. We apply on the same pair of knots, and if this we are lucky, it may distinguish them, then somehow that's how we try. So classical invariants of knots are the Alexander polynomial, as I said, the knot complement, and also the fundamental group and the homologous groups of the knot complement. 3 colorability, Jones polynomial. 3 colorability means if it is, if we can color throughout a knot diagram with 3 colors, so that either all 3 meet at 1 crossing or just 1 color meets at every crossing. Okay, and we have to use all 3 colors, and it is proved to be a knot invariant. And how it is proved? We use the Reidemeister theorem. That's why it is very important that we have discretized the knot equivalence. So for proving that some function is not invariant, we just have to show that it respects the three Reidemeister rules. Okay, so, and then we have the Jones polynomial, and from there start the quantum invariants for knots and three manifolds, the Witten theory, the Reshetik and Turaev. I drop names because you will have heard of some names, but of course you are not experts in the theory, so I don't expect you to understand what I'm talking about. Then the Vasiliev invariants, we have the Kovanov homology, quantities by quantities, and so on and so on. Let me also draw your attention to some applications of knot theory to show how much of ramifications this area of mathematics has. For example, with planar graphs there is a dual connection. Every knot diagram gives rise to a dual graph where the regions of the knot are like a chessboard shading, and every face corresponds to a vertex of the graph, and according to the crossing here, the type of crossing, if it is, let's say, positive type or negative, we give a sign. So we have sign planar graphs, and we have a total analogy between knots and planar graphs and networks. And in fact, it is proved that the electrical conductivity is a knot invariant for a circuit, for an electrical circuit. It is very interesting, using Kirchhoff's laws. Another application of knot theory to graphs in three space is the following, that if we have a Kn, the complete graph on n vertices, so we have n vertices, and every vertex is connected to every other one. And we have an embedding of this graph in three space. So the arcs could be knotted, could do anything strange. Okay. However, the theorem says of Conway-Gordon that any embedding of K6 with 6 vertices will contain a non-trivial link. No matter how it is embedded in space, the graph, it will contain, we will always find a non-trivial link. You see here, those two triangles, they are linked together. And for K7, it is more difficult to prove that every embedding of K7 contains a non-trivial knot, which is like a Hamiltonian cycle of the graph. These are very interesting theorems, show the deep connection between knots and graphs, and here's another connection of knots with graphs. We have application to statistical mechanics, and this came up only after the discovery of von Jones. Before, we had no idea about these connections. The Potts model, which explains the melting of the ice, has a partition function. That means we find the Potts model, when we consider it, we oversimplify the model that it is only planar, and we have the vertices here, which are the molecules. The assumption is that only neighboring molecules interact, so we have an interaction energy, and when they are far away, not connected, then we assume zero interaction, and then we have the energy function of a given state. And when we say state, because each molecule has a spin, so we have a modular spin, Q, modulo Q, and so a given state for the ice, let's say for this model, is that we assign to each molecule a spin, and then for each state we have the energy function that is based, the sum of all interactions, neighboring interactions. Then we have the partition function, which is exponential of this energy function, and then we sum up over all possible states. So this is statistical mechanics, statistical thermodynamics, and how this is the idea in this kind of models. And it turns out that this partition function satisfies the recursive rule of the dichromatic polynomial, or the TAT polynomial for graphs, which is another manifestation of the Jones polynomial, which is really something unexpected. Also in polymers, and so the chemical engineers are interested in constructing new materials which from given molecules, they want to construct new materials which have some, retain some properties, but they have some new properties also that are better, like lighter or more elastic or whatever. So one type of such molecules is what we call topological isomers that have the same abstract graph, but when they are embedded graphs, one cannot be isotoped to the other. So we call them enantiomers, which are mirror images, like a mirror between themselves. So it is important to decide theoretically if two molecules with the same abstract graph are topologically equivalent or not. We can decide because we have the invariants, the not invariants, and we can tell the chemical engineers if they're isotopic, don't spend money and time in the lab because you will not gain anything new. If they are not isotopic, then perhaps it is worth trying to develop this material. So we can give some input. Another application is in the DNA noting and recombination, where we have the site-specific recombination. The first experiment took place in Berkeley in 1989, I think, with Sprengler, Sylvia Sprengler and Nicola Tozzarelli, who made a repetitive site-specific recombination. Means that in a particular site, something happens, the topoisomera of type 2 go and cut the double strand of DNA, and they reconnect in some strange way. All this happens in DT, so here is like a black box. And then it creates as an outcome some node. We see only the outcome in the laboratory, and then in the same site there is the same recombination happens, we get another product node, and then the question, and plus the third one, and the question is, what happened in this black box in that time? And they decided, they found that with a tangle model, using a theory, topological theory of ciphered manifolds and the classification of rational nodes by Schubert, they answered what is the recombinant here and what exactly this experiment did. In other words, they said that if you give me the first 3 outcome nodes, then I can tell you if the experiment runs forever, I can tell you the rest outcome nodes in the future. And then we had more of this, but that was the first one, and that was also very impressive because it used the theory of rational nodes, as I said. Then molecular biologists became very interested in this, so they were wondering about the classification of rational nodes, which somehow used the classification of length spaces, so the molecular biologists could not really understand. And that was when Kaufman and I decided to try to give a combinatorial proof of the classification of rational nodes. And we were lucky because the tight conjecture at the time was resolved about alternating nodes. So we were able to give a combinatorial proof which was more accessible. Another subject related to knot theory, directly related, is the theory of braids. Gauss was also interested in braids, and he drew this picture in one of his handwritten notes. By the way, these notes are in the old library in Göttingen, in Prinzenstrasse, and they have all manuscripts of Gauss. It's really very interesting to visit and check on these handwritten notes of Gauss. Again, his interest was of course, although I can understand some German, I lived for 4 years there, but still I cannot decipher what this says. Yet I can understand that it is through the theory of electrodynamics of curves in space, somehow, because through this then he came up with the Gauss linking number, which is this integral over a closed curve or an open curve in space. Anyhow, for us, braid is a topological object. There are n strands. Here we see 3 strands running from joining n top points to n bottom points. so that they run monotonically, and we have only double crossings where we give the information over or under. So this is a braid diagram, and clearly if we close a braid diagram, we obtain a node or a link according to, you see, a braid, the braid group subjects on the permutation group. So the cycles of the permutation, the disjoint cycles, in fact the orbits of the permutation, are the number of components in the closure, of the link in the closure. Okay, what I'm trying to say is that because it is monotonous, we have a natural orientation from top to bottom, and of course we have what we call a braid axis, that the braid, if it is closed, runs around this axis in a, let's say, positive sense, a counterclockwise sense. And another way, we can imagine the axis running behind the flame of the braid diagram, and then the yarn goes around this line, which is the axis. Okay. Now, the reason I mention braids is because, as we know, we have the Artin braid group with elementary generators, which are the elementary crossings and the inverses. And so we have a very nice presentation, which then leads to the question whether we could make the study of knots, whether we could translate knots from Reidemeister and discretized to algebraic using the braid group. Indeed, Alexander proved that every oriented link diagram could be isotoped to a closed braid. So we can always do that. So here we have the center where the axis passes, the axis of the braid. We take any point on the plane of the diagram, and then we say if arcs go in the right direction about this point, we don't touch it. But if it changes the orientation, here for example, we don't like this, 1, 1 prime, then we have to change. But we have to change in a way that is consistent, that it is isotopic. For example, 2, 2 prime, you see this back, this arc that, we can imagine arcs like elastic, small elastic arcs that can be infinitely extended. So we take this and we pull it underneath. This goes under here. So we pull it underneath so that it goes all the way under the rest of the diagram, but beyond the axis of the braid. So now it goes in the positive direction, you see? This is the idea of any braiding algorithm, as we say. What we keep here is that every, from braids we go to knots with a closure, but vice versa, from knots we go to braids in this way, closed braids. Here was my first contribution when I made an algorithm for braiding and giving rise to open braids, like algebraic braids. And we have proofs by Johan Berman, Hugh Morton. After the discovery of the Jones polynomial, we have many proofs for the braiding. Now, okay, now we know that we have an interaction from knots to braids and back. The question is not isotopic. Can it be translated into some kind of braid equivalence? And the answer again is yes. The first thing we observe here is that if I have a braid A, and the braid that is conjugate of A, I conjugate with some crossing here. When we close the two braids, you see that those two go in the back there and they cancel each other, those crossings. It is a Reidemeister 2 move. Therefore, the two braids are conjugate in the braid group, but their closures are isotopic. So, conjugation has to be included in the equivalence relation of the Markov theorem. Then the other thing that we observe is that if we have a braid on A strands, and we make here another crossing at the bottom, adding one extra strand, and close this, now from a braid group Bn, we go to a braid group with one extra strand, we even change group, it's not even conjugation in the same group, but we change, yet, if we close, we see here this loop that cancels because it is a Reidemeister 1 move. So this move has also needs also to be included in a statement of braid equivalence. Markov proved that these moves are sufficient. In fact, we are cheating here. Markov gave 3 moves to start with, and he proved his theorem. Of course, the proof of this theorem depends on what algorithm you use for braiding a knot diagram. So, Markov stated the theorem with 3 moves, and then his student Weinberg, Nikolai Weinberg, reduced it to those 2 known moves using Alexander's algorithm. John Berman filled details and made more rigorous Alexander algorithm. Benekin used 3-dimensional contact topology. This is really a very central theory, knot theory. And then Morton, after the discovery of Jones polynomial, we have 4 more proofs, and with different algorithms. And one proof that I gave with Colin Rourke, we reduced the Markov theorem with just 1 move instead of those 2, conjugation and Markov stabilization. Now, this, and I'm showing you this, this is called the L move. And this consists in the following. At any point in the braid, you cut, at any place in the braid, you cut at some point the strand, and you pull the lower end upward, the higher end downward, and you have to be consistent both under the rest of the diagram or both over the rest of the diagram. And we create this way a new pair of braid strands, and it is still a braid because the move respects monotonicity. And if you go and take closures, you see that what you did is just that you took a small kink and you just pulled somehow. So it is an isotopic. It is like a big and extended generalized Reidemeister 1 move. But it is a combination. The reason this is important is not because we have a 1-move Markov theorem. From this it follows, of course, that conjugation and the Markov moves, the stabilization moves, follow from the L moves, can be constructed by L moves, and vice versa. The importance of this move, which was discovered much later than that, was that we can make with L moves, we can formulate braid equivalence theorems in any diagrammatic setting where we have knots, like knots in 3 manifolds, knots in knot complements, knots in handle bodies, knots, virtual knots. We have the virtual braid group, singular knots. We have the singular knotoid, and the L move, well, the knotoids that I'll come right after, and anywhere where we don't have braid structures, because you see, the Markov theorem used the fact that we are in a braid group. So there are situations where we don't have braid group. We have a monoid or no group at all, no algebraic structure at all. So the L moves proved very fundamental and came handy to formulate at least geometrical equivalences, and then whatever algebraic structure we have, slowly we can turn it into algebraic statements. But we have a first if and only if, which is important to be based on. The Markov theorem was used by von Jones for the first time with Hecke algebras, which are quotient algebras of the braid group algebras, to discover his seminal Jones polynomial. And so, which is much stronger. In fact, the Jones polynomial with 1 variable was through the Temperley-Lieb algebras, which are quotients of the Hecke algebras. And from the Hecke algebras, we have the 2-variable Jones polynomial. You may have heard of this as the Homfly polynomial. Okay, so these are the first strong, really strong invariants we had in hand, and then from there on, the knot tabulation problem really exploded, and then with the use of computers and now quantum computers, it has advanced enormously, the study. Okay, so knots classical knots are special cases, as we see, of the theory of notoids. So they are included. So all this big, what we describe the big theory, injects into the theory of notoids on the sphere. So this was developed by Vladimir Turaev in 2011. He defined a notoid diagram in the sphere or in the plane or in any oriented surface as an open-ended knot diagram with two endpoints that can lie in any regions of the diagram. So we have the first paper of Turaev in 2012, and then we have some students of Turaev in Indiana University who studied further some invariants. So this is the formal definition that the notoid is an immersion of the unit interval in a surface so that we don't make the requirement that the ends meet, so we don't get knots. And in the immersion we give the information of over or under at crossings, like we did in diagrams. The endpoints, the image of 0 in this immersion is called the leg, the image of 1 is called the head, and so we have a natural orientation for a notoid from the leg to the head. So let's see. So here, so this is the image of 0, and it goes from the leg to the head, and here from the leg to the head. Okay, this is a notoid. And the equivalence on notoid diagrams is like the Reiter-Meister moves, because we want diagrammatic. You see how handy comes now, the Reiter-Meister theorem. Plus, we want this extra move, which we call swing move, because the endpoints could move. But they can only move within the region. They cannot surpass the region of the diagram, because then it is not equivalence anymore. In other words, we have the forbidden moves that the endpoint is because we have the forbidden moves. Otherwise, everything would just come to nothing, would resolve to just an arc. So I will skip this. Turaev showed that there is a surjective map from notoids to classical knots, and this is induced by connecting endpoints. So this is supposed to be red, but it does not show very clearly here. So we decide that we join the leg with the head with an arc that runs, simple arc that runs under anything in the notoid diagram, and we call it the underpass closure, and equivalently we have the overpass closure. So, because we have a surjection, this means that whatever invariant on classical knots, it can be computed on the level of notoids. And this means that, and that was the motivation of Turaev, because to compute knot invariants, most of the knot invariants, their complexity increases with the number of crossings on the diagram. So, if we have here representatives with, suppose this crossing is missing, okay, in the notoid, but if we know that this notoid represents precisely this knot type, then we can compute the invariants on the notoids with less crossings, because this is open. So we reduce complexity exponentially in the computations. That was Turaev's original motivation, and it was a strong motivation for developing the theory of notoids. And then he went on to define some invariants of notoids by using the invariants on the classical knots that they represent through this underpass closure. Omega 0 is the underpass, omega minus, omega plus is the overpass, whatever we choose. So, if we have a classical knot, we have the fundamental group of its complement, which is a knot invariant. And then we define if K is any notoid whose underpass closure is that knot, then we define the fundamental group of the notoid to be exactly the fundamental group of the knot. Okay, then using, they also derive with the students that we mentioned before, they also defined the genus using the theory of notoids with less crossings. They managed to find better bounds of the genus of the knot. The cipher genus of a knot is the smallest genus of a ciphered surface of a two-dimensional surface where the knot can live in, can be embedded. So like the torus knots live on the surface of a torus. Okay, so we have the minimal genus, it's called the ciphered genus. So they found better bounds for the genus of knots through the notoids. Now, we said how we go from notoids to classical knots. Now we also have the way to go from classical knots to notoids as follows. If a notoid has its ends, both ends, in the same region of the plane, like here, for example, then we can join, you see, the endpoints without meeting, without crossing anything. So these knots which we call, these notoids which we call knot-type notoids correspond bijectively to just knots. That's how then we can view knots as notoids. And of course you will tell me that this is not equivalent to this because this is the outer region, this is the inner region. For this reason, Derive made his theory for notoids in the two-sphere. So his diagrams, notoid diagrams, lie on the two-sphere because here we have this extra move that an arc can swing around the two-sphere. So those two are equivalent. Whilst if we see those two diagrams on the plane, they are not equivalent. And there is a reason that I say this. So we have an injection. So notoids on the sphere are like knot-type notoids that are in bijective relation with knots. And we also have notoids in the plane. So we have that knots, and I mean knot types and link types, inject faithfully in spherical notoids by Derive's theorem, notoids in the sphere, which in turn inject bijectively to planar notoids. In other words, from this, classical knot theory injects faithfully into notoid theory in the sphere, spherical notoids. So we had one problem of classifying knots, now we have another problem of classifying spherical notoids, which is much harder, and yet another third problem of classifying planar notoids, which is even harder. And I will try to convince you why these are useful. So, let's see. Here, yes, so we have the knot-type notoids, where the ends lie in the same region, or they may be related just by itemized moves. They look like different regions, but they are really the same here. So this is a knot-type notoid. In fact, it is a trivial notoid. And here is on the plane to make them come in the same region because of the forbidden moves. So this is a notoid of two crossings. We don't have knots of two crossings, only three. But here is of two crossings, which is not trivial. And we would like, of course, to develop invariants that will distinguish notoids, spherical and planar. And invariants of knots are not good enough because the invariants of knots will distinguish only these knot-type notoids. But then we need to extend the theory. So, of course, we have, I will go now, I need to go a little faster, but Derive not only the fundamental group, but he also extended the bracket polynomial, the Kaufman bracket polynomial, which is the regular isotopic counterpart of the Jones polynomial, that is invariant only under two moves, the Reiter-Meister 2 and 3, that is related to framed knots. I will come to this in a few slides. And framed knots are important because with frame knots we build any three-manifold, closed, connected, oriented three-manifold with topological surgery. And this is related to the Poincaré conjecture. So for studying three manifolds and quantum invariants, we talk about framed knots. Framed knots, they don't use the Reiter-Meister 1 move, it changes the framing. So for framed knots, we use only Reiter-Meister 2 and 3, and that's why I said that the Kaufman bracket polynomial is the framed isotopic counterpart of the Jones polynomial, which is ambient isotopic, all three moves. I guess I have lost you at this point, but I will keep going because I don't see people sleeping, so one of the invariants of notoids that was, is it strict? Is this totally strict?
No.
Okay. One of the invariants of have complexity 1. Here we see complexity 2, but it is very tricky to compute complexity because we need to find over all possible diagrams the minimum number. So by definition, when we say over all possible, the minimum number is an invariant, but to compute such invariants, so for such definitions, it is easy to say that it is invariant because by definition, but to compute is very tricky usually. So okay, notoids revisited. So how do I come into this theory? I was in 2011 in a conference in Switzerland, quantum topology conference, by the Lake Thune, when Turaiv presented, I think for the first time, his theory of notoids. His paper, remember, was in 2011, was appeared in the Osaka Journal of Mathematics. And at the time I was working with Eleni Panagiotou, my PhD student, on studying topological entanglements of polymer melts and developing topological ways of distinguishing polymers. And Ken Millet, who was visiting from University of Santa Barbara, California, he was visiting Stasiak at the time in Lausanne, so we got all interested in this problem. When I heard Turaiv, I immediately could see that the theory of notoids, because polymers are open-ended curves, usually they are linear, like DNA is usually a linear molecule. In vitro, sometimes they manage to make, or very few in nature, DNA molecules are closed, ring polymers, but usually they are linear. So then we had a big grant of excellency, the Grant Thalys, and Lou Kaufman was the visiting researcher of our grant in the research group, and Neslihan Gugumcu was a new student from Turkey. So she reached out to me, and I proposed to her to look into the theory of notoids, and so she started working with Kaufman on new invariants, and with me she developed the theory of bredoids, which are totally structures with no algebraic structure whatsoever, and very interesting. So they defined the arrow polynomial with Lou Kaufman, where at crossings we make oriented smoothings. I will skip details. Here is some computations, just the arrow polynomial. and they show that it is a notoid invariant. Okay. In fact, it is we need normalization. It is a regular isotope invariant. So, this shows what I told you before, that notoids in the plane, so the notoids in the plane generalize faithfully notoids in the sphere. Let's go. I have a reason for showing this. Kaufman and Kukurchuk did the following. They found a representation of notoids that are on a surface, on the plane, for planar notoids especially. They found a way to lift faithfully to curves in space. And this now becomes very interesting. As follows, they take two parallel lines perpendicular to the projection plane of the notoid, and they make the endpoints, just like rails, they are free to lift, and the curve also lifts in space so that it projects to this diagram, and they show that there is a bijection between planar notoids, that means equivalence classes of notoids on the plane, and line isotopic classes of such open curves in space with the rails. That was very important because it led to a direct application. For analyzing proteins usually they are open chains. In previous approaches for the topological study of proteins, they would do either a direct closure, that means they would connect the two endpoints of the protein, and then they create a knot, and then they study the type of this knot, and they say that whatever properties, then it is property of the protein. Or they use the uniform closure, that means we enclose the protein in a ball big enough to have everything in there, and we take any plane, tangent plane to this ball, to the sphere, and we project the protein using the two parallel lines. We create parallel lines tangent to the plane, and we project. And then the projections are notoids, of course. But the uniform closure was that, okay, that is the notoids, okay, but the uniform closure was that they choose any projection plane, so the two ends of the protein, they have the two ends, they intersect the three ball, and then they join. On the three ball, they join with a simple arc. The protein is inside there, so there is no intersection with any other arcs of the protein, and this is what they call uniform closure. And they make millions of these. They take how many thousands of projection planes, and for every projection we get knots. We will get different knots usually. So all these different knot types characterize the protein. So the more knot types we can find for a protein, the more we can characterize it. And this has to do this has to do with this big project of protein map, what they call protein atlas. And a third approach was using the virtual closure, where when they connect the two ends of the protein, they declare whatever new crossings as virtual crossings. A virtual knot theory was developed by Kaufman in 1989, and a virtual crossing has no information under over. It is considered under and over. It is like a permutation crossing. This is virtual knot theory, which is also a very rich subject in. So we could also declare the new crossings when we end as virtual crossings, and then apply virtual knot invariants for identifying the knot types, the virtual knot types. And we thought of using notoids. So my student Kundaroulis Dimos, he got a postdoc. He was working with me on something totally algebraic, fremization of temporally lived algebras, and he went to the lab of Andrei Stasiak in Lausanne, and he proposed to use notoids for the study of proteins. So they first used spherical notoids in the study, so they project the protein in 500 directions and see what knots they obtain. And when we came in, we used planar notoids, and see the difference. The difference is really very spectacular. So when a protein, the same protein, 3kZn, was studied first with uniform closure, we got these knot types. You see, 1, 2, 3, 4, 5 knot types, including the unknot. So this set of knots is an invariant of the protein, topological invariant of the protein. When Dimos and Andrei used the spherical notoid approach, they obtained these knot types, substantially more than the uniform closure, more information about the protein, and but the information it renders this with the study of spherical notoids is as much as the virtual closure, using the virtual knots. So when we collaborated with this group, we used the planar notoids, and look how many different knot types we get for the different projections. Really much, much richer for this protein. So this set of knots really tells something about the protein. Okay, and then we also made a topological model for bonds, because the proteins also have locally bonds, so we developed in the same paper bonded notoids, where in every site of bonds we replace it with a vertical clasp if they are anti-parallel, or with a horizontal clasp if they are parallel, and this way we were even able to distinguish more information about the protein. Because here you see the protein, if we forget the bonds, they are just trivial arcs. But with the bonds replaced by clasps of crossings, they are non-trivial. So this also gave some extra information to those people who want to study and classify proteins. And this will be the last part. I have much more, but this will be the last. When we look at linear DNA, then proteins, DNA tends to make, with their combination, it makes non-trivial knots. But the DNA has this double helix, and the double helix, if we represent the DNA molecule by just a single strand and go into knots, or a notoid for a linear DNA, we miss the double helix information, which is really framing information. And I mentioned framing before. So, Wout Moltmaker from University of Oxford, a PhD student, he developed the theory of framed notoids by using Tourai's bijection of spherical notoids with simple theta curves, I will not say more, to a bijection of framed spherical notoids, where the notoid, the crucial part of the information, is a band and has also framing. And so this is much more, it captures much more information, so this is really more appropriate for studying DNA. Then I will just say that with my colleague Dimitrios Kotokostas, we developed the theory of rail notoids, where now we project rail curves in space, not to the perpendicular plane, but to the plane of rails, and this is yet a new theory of rail notoids. I will go fast. And when we connected with the knot theory of the handle body of genus 2 and used some algebraic rules known, and with the Sikhan, as I said, we developed the theory of bredoids, which is also very interesting because we made the analog of the Alexander, the closure for the bredoid, the Alexander theorem that every notoid can be turned into a bredoid, and also, let me go fast, and also the analog of Markov theorem. And here it was really handy because we don't have, as I said, group structure. We don't have any algebraic structure in the set of bredoids. It's a very difficult object worth studying algebraically. So here the L moves came in very handy, because at least we have an L equivalence. We say if and only if. So that's a good statement formulation for as much as we have for structure so far. So this is really crucial, let's say. I think I will stop this part here because it goes on, but I will stop this scientific part of the talk. Thank you. Thank you very much.
Do you have any questions? Please.
I should like to ask you, from historical point of view, the birth certificate of the theory of knots comes from Gauss. This means 18th century, 19th century. In fact, who was the first group of mathematicians?
Gauss copied these notes from the Naval Academy of United Kingdom, who studied, had the knots as sailors' knots, that's all. But Gauss was interested in curves with electrodynamic properties, let's say, and how they behave in space, and he took curves bearing electrical, charge. So I guess he started looking at, he wanted to have knotted orbits, but with from the electrodynamical point of view.
So my question is.
So it looks like it goes back to Gauss and Lord Kelvin.
So this means 18th century.
Yes.
Okay.
Early 19th century. Sorry. 1830 or something.
My last question: if you have a knot and you project it on the plane or on the sphere or any other surface which is convenient for you. All properties, all informations you obtain from the projection, from the graph, allows you to recover the knot, or that's impossible. You start with the
projection.
You obtain a diagram, a projection, and you consider from a mathematical point of view all information of this projection. This gives you the possibility to recover uniquely.
Absolutely, absolutely. If we have the diagram and the projection, and we declare when we see the projection which is over at every side, at every double point, we have to declare, and then this bears all information for the node.
And this happens not only for the projections in the plane, but also in any surface.
In any surface we have knot theory. This is also not studied yet. We have knots in thickened surfaces, and there is studies going on, like braid structures in thickened surfaces, corresponding groups, and so on.
Thank you very much.
Yes.
Other questions?
So, yeah.
I was just wanting to verify that when we were talking about noctoids and the leg and head being in different regions.
Yes, the endpoints.
Yes, the regions are connected components of the complement.
Exactly. Yeah. Like with the graphs, the dual graph.
Yeah.
The faces. Yeah.
Exactly.
Where the vertices go.
And we have.
This is what we call the checkerboard shaping for us. Yeah.
Okay. And do we have any information on the complexity linked to the topology, the knots?
Of the knots, of the notoids?
Yes.
No, I don't, but this is much more complex than knot theory, which is NP hard. So this is much harder, I guess, to classify. Proper notoids in S2, it's much more than just notoids, than knots, much more. And it depends on the complexity. If the complexity is 1, then it is one step further. It's like a gradation. The complexity is a gradation. Complexity 0, classical knot theory. Complexity 1, we have to classify. Complexity 2, new classification, and so on. And if you go to planar notoids, it is much harder to make. Yeah, because two spherical notoids, let's say two different planar notoids may come from the same spherical, because we can just move around the sphere. So the last thing I wanted to just, if we could put this other small thing, just to say, because it is a meeting of women in mathematics, so I wanted to just say that last year we started in Greece to have also Greek women in mathematics, a new union, I don't know, the GWM. So I just wanted to say, I don't know, can I, okay, full
Just a
screen?
second.
Sorry. So, and we started, I mean, we made it a year ago, and we started all our activities all in 2022. Here is like the image of Hypatia. Yes, and okay, and we had, can I?
Yeah.
Okay, then last March we had our first podcast. Here we have some amazing young women in mathematics. Here is Maria Vlasiou in Eindhoven and Twente in Holland. Here is Valia Gazaki, who is in Stanford, I think. Here is Polixeni Spilioti, who was in Argus and now she's in Göttingen. I call them all super girls, and the girls also in our department. So we had our first post. I cannot go. Can we change? Then we celebrated May 12, the celebration of Miriam Mirzakhani's birthday date with an online soiree of mathematics with two invited speakers, Hara Haralabous, who is the chair of the Faculty of Sciences in Thessaloniki, and with Efi Kalfayani, who is in the Michigan State University. That was very nice also activity. And then last July, we can go to the next, or can I go to the next? Last July we had our first workshop of Greek women in mathematics in my university, the National Technical University of Athens, with lots of invited speakers. It was a great, really great event, and the round table, and and then the round table, where we found, of course, that the higher posts women in mathematics seek, the more difficult they can get into. We know all that. There are some things there to make better, to improve. Here we are, the group. And we also had the exhibition Women of Mathematics throughout Europe, with the extended exhibition where I know somebody here who it was in, her portrait. I don't know if I have you here as a sample. We started with 16 portraits in 2016 in Berlin, in the ECM. And then when they announced that the 2020 ECM will be in Slovenia, Slovenian women asked to extend this exhibition with women from the Mediterranean shores, so from Mediterranean countries. So we had some extra portraits. These are all from the 16 first. And here is the expanded exhibition. And yes, so, and I was very honored to figure in one of these.
Oh.
And how, yes, and I want to say also that I represent my country in the European Women of Mathematics, and we would be very, very happy and interested to have any joint activities with other networks of women in mathematics in other countries.
Thank you.
So, thank you very much.
Thank you. Break, and we will have like lunch served in room 278 on the second floor. So we can go together on the second floor again. There is one jacket which is left in the hall where the opening was. Somebody forget his jacket.
I think.
Okay.
Който искал на него да викам, как ще ми
За кафето да ти излъгна.
И аз винаги така съм си мислил.
Муж. Сын на него похож или на меня?
Да.
Да, на него. В том году сын был лучший украинец, баскетболист. На всю Украину больше всех очков. Как это? Спорт называется.
Okay. Do you communicate? Yeah, it's fine. Nothing to worry about.
talk on mathematical formalization and mathematical modeling in biological sciences, please.
Okay. Thank you very much. I put here the black sheep because in your high-level mathematical community, I'm a black sheep because I will not talk about high-level mathematics as all of you here. I will talk about mathematical formalization and modeling, which is usually does not need very complicated mathematics. The main art in this story is to find a proper mathematical tool to attack important biological problem. And my work connected with, I would say, the most exciting and most intriguing problem in biology. It is formalization of embryogenesis. So the question about building the geometry of a new organism, and I will tell you about several parts of this complex problem. We will start from the point, which all of you of course know, that geometry of any organism is very well determined. So you have the geometrical shape of the parts, ears, tail, and so on, the parts of the organism in the proper places, in the proper coordination which is each other, and the whole organism also well determined. And interesting point that each of these organisms starts from one cell, yes, from one cell which named zygote, and this cell divided into 2, into 4, into blah blah blah, and then you need to know, and of course you know, that when cells dividing, it have the same DNA in all cells. So DNA in the cells of your eye and DNA in the cells of your stomach are the same. And on the other hand, your eye is an eye and the stomach is a stomach. And how, starting from one cell, the proper geometrical shape is achieved is a very big mystery which is not known now and which we try to attack both by biological and by mathematical methods. Interesting fact that if you look at the normal development, the geometry, not only in the final shape which I showed you, but at each step of the early development is very strictly determined. The cell divides first like this, then like this, then like this, and so on. These cells start to grow, these cells not growing. So from the very beginning, we have determination of the events. Like in animals, so in plants. We can say that, okay, each cell from the very beginning has some information, blah, 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 blah. No. Because individual cell fates are not determined. We can have a lot of interesting experiments, and of course you know it also, when we separate tissue of an embryo for individual cells, or we have the process of regeneration, or some other processes, individual cells can change the determined way to which they are committed in the previous normal determined way, and create completely new but very determined structure. So the cells know the final shape of an organism or of a part. For example, here, one cell from the embryo already committed to some specific tissues were separated, and it managed to give a normal development. Here, the developing limb of a frog was divided into 6 parts, and each part, which has no connection with others, produces its own leg. Normally, it's supposed to produce only part of the leg.
So cells in this part manage to change the determined way and by different morphogenesis pathway create a proper determined pattern. This is a great mystery again. So this is the same in the case of regeneration. Okay, so the idea on which we work for many years is to find a plan of determined geometry which is supposed to exist somewhere in living organisms in the same way like we have a plan for architectural building. And we need to understand where in cells, by what molecules, this information is somehow coded, exists, I would say the word coded, how this biology to geometry translation occurs, and what is the laws of this translation. So how the plan, if it is exists, implemented into the real organism, which is real geometrical parts. I would like to emphasize again, because it is very often questioned, genes. Genes and DNA, first of all, I already told you that DNA is absolutely the same in all your cells, okay? And genes, which is in DNA, they do not code the geometry, it code proteins. Gene account only for protein structure. Also in DNA you have regulatory parts, but these regulatory parts also determine only concrete protein yes or concrete protein no. So DNA, genes, code proteins, but a set of coded proteins does not make even a cell with all its geometrical form and all its specific shape, not even say about other patterns. So genes and corresponding proteins provides material, stones, for create the proper patterns, which is somehow dictated for some other information, for some additional layer of information. If we come to this analogy, we will say, of course, if you don't have stones for the 5th floor, or you don't have stones for the tower, you will not have a tower. Of course, there is a proteins which is responsible for 5th floor of a tower, but it should be a plan which will say, yes, in this place, please give me protein 1, and in this place, give me protein 2. So differential gene expression, so the fact that genes in different places produce different proteins, supposed to be somehow dictated by some other layer of information. And the theoretical idea on which we work for a long time, for now, is that the concept that the geometry of biological objects, the geometry, the precise geometry, is coded by epigenetic information in a cell. Epigenetic information means additional to genetic. Epigenetic, not instead of genetic, but additional to genetic. Genetic, of course, is very important, but it is other type of information. And another idea is that to have a mathematical formalization of the process in order to find the proper laws for this, we formalize development as a developmental graph, which is a rooted tree. This is zygote, the first cell of the organism. Zygote is divided into 2 cells. These cells, for example, grow, this cell divide again, and so on. So we have a developmental graph with cell states. It's not exactly the cell, I would say, and cell events, which is edges. So cell state is information about cell. In the simplest way, it is a position in the embryo, cell position in the embryo according to embryo axis. And this is epigenetic information. In our current work, we formalize this epigenetic information as a 2-dimensional matrix. this why it has this shape. And cell event is any change of cell state. So one cell could be in different cell state. It can grow, it can differentiate, it can undergo apoptosis. Apoptosis, it is programmed cell death. It is very interesting that for creating the final geometrical pattern, some cells in the organism undergo cell death. For example, to have an empty space when it is needed. For example, like this, we have our hand. This part, first we have a full hand, and then this part undergo death, apoptosis. So we formalize cell events as cell division, cell growth, cell movement, apoptosis. Internal cell event, one of the examples is differentiation. Internal cell event is changing of epigenetic information in cell without external other events. And if we have this information from experiments, but for now, unfortunately, we don't have enough epigenetic information from our experimental work. If we have this information to each cell as a part of its cell state, we should add epigenetic information. And this information, of course, supposed to be changed, unlike DNA, after each cell event. After each cell event, this information changes. Because of it, in different cells, we have different parts of epigenetic information from the first cell zygote. And this drive next differential gene expression. And we try to build our theory on these developmental graphs. How these developmental graphs, which connected cell states and epigenetic information which involved in next cell event, how it is connected with the final shape of an organism. We have an idea that the graph of adjacency built on the leaves of the developmental graph, starting from zygote, at any time point will account for the shape of an organism. Here there is kind of embryonic organism. We connected with ages the neighbor cells. We have graph of adjacency. So here we have graph of adjacency built on the leaves. Please ask questions if you want to clarify or understand something better, because I want you to not to be lost. It is clear. It is clear. Okay.
At every stage, you just increase the graph. It builds up.
Yes. Every minute, no, not every minute. Actually, in every 24 hours, zygote divided into two cells. Then this cell grows. This cell again divide. So, and in time t, we have, for example, here in this example, 7 cells. And the graph of adjacency of the cells will be will show the shape of an organism. It will show the shape in the language of graph of adjacency, because like small elephant and big elephant have the same shape. So we don't say about the length of these ages, but we say about the adjacency of them. So how they located one related to another. So our main goal, on which we work many years, and I have this opportunity to have this presentation now, to invite all of you who would like to discuss, to have collaboration, to have some kind of activity, to join us, because this goal still exists. So we want to find a set of rules given by nature which act on cell states and result in a particular cell event for this cell with this epigenetic code, which will give this developmental tree which lead to invariant final pattern. The initial idea which was worked and changed and then returned back, was that we can explain, we can start to formalize it in a language of fiber bundles, which has the developmental graph as a base, and in each corresponding to each cell state, we have a fiber with internal information. So the pathway, because this is a pathway leading to environmental morphogenesis outcome, shape. But on this way, we have a lot of mathematical problems, and I just want to show you this smell of what we are trying to do. We have several papers with these ideas and mathematical implementation. I'm not satisfied with any one of them, and because of it I don't want to talk. I just want to give you a general idea and invite again to work together on this problem. Meanwhile, what we have done as some parts, some stones of this structure, morphogenesis pathways structure. We built a morphogenesis software, computational software, which create one cell, normally zygote, but it can be any other initial cell, and we can introduce epigenetic code by hands. It is not from experiment, we don't have experimental data, but we can put whatever we decide. And then this morphogenesis software, according to some rules which we invented, according to some biological ideas, I will show you briefly these rules. Again, I'm not satisfied with these rules, it is just initial step. But however, the initial cell, according to this rule, start to produce cell events based on this epigenetic information. And you see the tree and the corresponding embryo, which at each time point are built according to this tree. And different colors account for different state of differentiation of the embryo, because and for this we already have a rule. So, briefly, the first rule is a choice of cell event. We have an idea that epigenetic information is supposed to spread in the cell, and its spatial distribution has very important significance. So all this is belongs to this details of spatial distribution of epigenetic code. So the choice of cell event depends on some rules of this distribution. Very important part is the rule for filling in new elements of the matrices, because as I said, after each type of cell event, epigenetic code is supposed to be changed, and it changed in a way that half of new cell has the same half as in mother cell. The cell divides, then half have a mother information, and other half is filling in according to the formula which also connected with the epigenetic information of the mother cell. By this, we can account for the situation of, for example, regeneration, when cells return back to initial information from which they can start to build the new structure, because they have already some information from zygote or from mother cells conserved. And this is a rule for differentiation. Okay. So even with this, or maybe exactly because of this very simple rules, you can see that our morphogenesis software is very powerful instrument to work with ideas, for example, with rules which we try to assume for this or that embryogenetic processes. You can see that here it is real actual embryo of plant embryo, one of the plants, and it is corresponding developmental tree. And here is the same developmental tree and shapes from our computational numerical embryo. So you can see that at least at the first 16 steps, it looks like good. And it is another species, another plant species, which was analyzed and built at our morphogenesis software result. So using this software, we can check some rules, and of course, we're waiting for biological experiments, and then we will put the information in this frame, and then we can manipulate the details of rules and see if we have a real thing or something wrong. Okay, in order to be able to compare these things in reality, we need to find how to compare developmental graphs, and from this algorithm of developmental graph comparison, we can also find some additional interesting things which are done and about which I can tell you with pleasure that it is done and get interesting results. Though for now without epigenetic code, just developmental graph with cell states and corresponding cell events. So, what is very interesting in all this story about determination of the cell shape? I showed you before that in normal development, all cell events from the very, very beginning are very, very strictly determined. Very interesting that it is absolutely not connected with phylogenetic information. Do you know what is phylogenetic information? It is evolutionary tree which was built according to evolutionary and relativity trends of organisms. And interesting that being determined so strongly in each organism, it is not anyhow connected with phylogenetic trees. Here it is shown phylogenetic tree of angiosperm plants, and here is the types of embryogenesis done in last century just because, according to the direction of cell divisions, and you can see that there is absolutely no correlation. Phylogenetic tree has its ranks, taxons, and this is absolutely randomly organized. And to make you laugh, even if you are sleeping, it is interesting to say that these early stages of development, very strictly determined, is the same in mammalians, so in our, and in nematodes, which is very simple worm. So there is no phylogenetic connection between us and worm, where we were a worm, and though these embryogenesis pathways in the very beginning, and which are very, very, very conserved and determined, are the same. And very different in birds, for example, and other organisms. So, why we have such strong, unclear problem? And our developmental trees help, at least somehow, help us to say what is going on, some ideas, can give us some ideas about it. So this is one developmental tree built on one plant species. You can see here, this is another one. You can see how different they are. So completely different cell events from the very beginning, and we find an algorithm for this developmental tree comparison. One idea was that we labeled, for now, because we don't have information about epigenetic codes, we labeled nodes by subsequent cell events. The second thing is that we compare graphs with the same depth. So we have, for now, only level 11. And we do node completion for each graph which has doesn't have nodes up to the level 11. Here I just show you completion of the level 3 and node completion for the level 4. And I will not stay for now for left-right information. If I have time, I will tell about it additionally. So the simplest matrix which we, the simple metric which we choose for comparison of this completed developmental graph is the cost of each change in the nodes labeled by subsequent cell events. So we have division in X plane, division in Y plane, division in Z plane, growth with coefficient C, coefficient of growth, internal cell event which without epigenetic code corresponds to just no cell event. We see that there is nothing happened with the cell, apoptosis, programmed cell death, and N stands for completed node. The node in one graph you have a real node, and in another graph you have N, which is a node which were completed during graph completion. And here is the price for each change, and this price was taken from the frequency of occurrence of this or that event. So it is calculated like this. And the distance between two trees is the distance between corresponding nodes, because after graph completion we have all the nodes like the same. So this is the distance between corresponding nodes, and this is a coefficient which accounts for the significance of level in the graph for the final tree representation. So because the information in different layers of the graph could be less or more important for the final structure of the organism. So this coefficient depends. It is a coefficient A which we check in normal 0.5, in power of the level. So in normal situation, not in normal, in initial situation what we checked, it means that with each next level the significance decreases. But we checked many other possibilities. So 30 plant embryos were investigated from zygote up to 11 level, and the developmental graphs for it were built with all coefficients, and the distance between each pair of them were investigated. Here is the table of this distance calculation, and we clustered these results using hierarchical average clustering to group those organisms which have close or the same type of developmental graphs in the closed groups. 30 plant species were taken from different ranks, different orders, different classes, and different families, so we can have representation for many different ranks. And here is the phylogenetic tree of all angiosperm plants. We take from it the corresponding subtree with the same 30 species which were investigated in our work and made mathematical analysis, not like in previous centuries. We just check how much our T3, our three clusters built according to structure of developmental trees correlates with the same 30 species in phylogenetic tree. And we have very small, no correlation, 0.18. So yes, we confirm that it is yes, no correlation, that developmental trees not follow the evolutionary or other phylogenetic trends, but what they can say us. So we analyzed the morphological characters of the adult organisms of the plant species, which were grouped in this case together. And very big theoretical and biological analysis gives very interesting results. We found that the initial cell events in the very early stages of embryogenesis, yes, connected with morphological characters which start to be visible on the organism much later during development. For example, here I mark this cluster group. This cluster group being related to different families, orders and organisms has the same structure of root, specific structure of root. And it is very interesting that this one is even from different class of plants. And this class has normally completely different root. But this, exactly this species has unpaired root, a little bit looking like another class, and it came into this group. So, not to be very long with biology, I just say that analysis of these clusters gives us very interesting results, that these early stages can account for details of type of root system, peculiarities of conductive system of plant, and the most interesting thing that they give morphological characters connected with special mode of life. Or plants can be heterotrophic, parasitic, and aquatic. And this separation into groups visible according to developmental graphs, which built for first 11 steps of morphogenesis. So this is interesting and encouraging results. So when we will have epigenetic information, we can say something more about it. But this is already statistically proved and very interesting. And the last interesting question, which we also analyze using developmental graphs, is what is the limit of allowed variability of the pathways capable to create a steady outcome within a system? Because initial steps are very well determined, but then after some point you have the different pathways, high level of variability depending on the organism, but all of these different pathways still come to the same outcome. So this is the main question, and we will not consider now the situation with high level, let's say fundamental variability, which is happened in regeneration or other crises. We will ask about normal variability, when, unlike situation with unique developmental graphs, some species can have different developmental graphs, but with the same outcome. So, of course, we have the idea that this variability depends on epigenetic code of a cell, And in case when we have strict determination, we have non-redundant epigenetic code. And in case of possibility to build a new structure, the cells has very much redundant epigenetic code with repeating parts. And in normal variability, local variability, we can have slightly redundant epigenetic code, which can be changed by the signaling from other cells. So we check this idea again using our morphogenesis software. We take the idea that normal pattern, the shape, can be evaluated by morphometric parameters, which is the relative, for example, length and width of the organism, or some parts, one according to another, or some angles. So reporting morphometric parameters of the object together with their allowed deviations, not altering a shape. So, and here is the tree and normal basic numerical embryo. Here you have different developmental trees which result in really very impaired abnormal embryos. And here we have epigenetic tree, developmental tree. These two cases when morphometric parameters, they looks like initial one, but we check morphometric parameters, for example, the relation between head and stem, and we see, or the graph of adjacency over head, and we see that they are very different. So they are out of the limits determined by morphometric parameters. And again, here we have different developmental trees comparing to basic one, but morphometric parameters measured on these objects give us the result that in this case we have variations of developmental trees which is within the limits, and all these variations we do by hands, varying little bit the epigenetic code of the organism. So the last slide, I don't again go deep into biology. We do it in parallel in experimental and morphogenesis software experiments. We have the idea that the existence and the shape of corridors of probabilities of different developmental graphs within the limit of possible creating of proper shape depends on sensitivity of a set of cells in morphological domain. And biologically we check the sensitivity of a cell. I will not go deep what is the meaning of this biologically, but this is the sensitivity to a signaling from the neighbor cells. So if the cells are not very well sensitive to the signaling from the neighbor cells, then the corridor of probabilities of the graph will be very wide. If it is very sensitive, it will be strictly determined developmental graph. This is what we showed, and this is my last slide. And thank you very much for your attention.
Are there any questions or remarks? I have a question.
Thank you. Not predictable after this huge amount of additional to my mathematics information, yes.
I would like to ask you something about the graphs.
Of course.
You said about something about graph comparison. You compare
Yes,
with some graphs. What is this graph isomorphism or something different?
No. It is like, look, we have a graph, rooted tree, yes? this structure. And we have another graph, and we have another graph which is completely different structure. So we have different cell events, we have different edges and construction of edges and nodes and so on. So we want to compare different graphs, how close are them or how far are them from each other. And we find and we consider this graph as a label set, because we don't consider the parameters on the edges, we consider the parameters on the node, and the parameter on the node is the parameter of the consequent cell event. For example, if this cell will divide, and if it will be divided in this direction, direction x, it will be direction, so it will be x on the node, the same y or z direction. And G is a growth. If cell, like here, growing, not dividing. Here it is not growing, it is the same coefficient. Here it is growing. Here it is 1, and here it is 1.2. So it is growing with coefficient 1.2. So we have a label set on a graph. And we also made a node completion. So if in one graph we have, I will show you the big graphs, okay. If, for example, in this graph we have this part, and in the other graph we don't have this part, we add, and in each point we add 2, because we should be able to account for the division. We add 2 edges, and then again 2, and then again 2, so in order to be able to compare. And then we compare 2 graphs which have the same amount of levels, we have the same levels and the same amount of nodes, and we just compare node to node with this price of changing. And then we summarize it all together, and the distance between graphs, with developmental graphs, is the sum of all distance between nodes according to these prices. And if we would like, we can add also a coefficient which change the weight of each level of the development in the final result of the comparison. This is how we it has nothing to do with the isomorphism of the graphs, because we exactly want to check the exact parameters of the graphs. This is our point.
Thank you.
And thank you for your question.
Thank you for the answer. Other questions, please?
In models for morphogenesis, there is usually a lot of emphasis put on the signaling and the molecular interactions. So I have seen, like, for the Drosophila embryo, there is
Yes.
this model with the reaction diffusion. Also for the zebra fishes, there is a lot. How do you see these models fit in the framework of the
Yes.
graph model?
Thank you very much for this question. I just briefly mentioned it, of course it was too much. Brief. Okay, so the idea of our work is that cell event of each cell, the future cell event of each cell, depends on its epigenetic information and the signaling from its neighbors. This is, I don't emphasize very much, but here it means in our work, and this was included in the morphogenesis software also, but I don't have time to talk about this specifically, but all what you mentioned, and thank you very much for this question, of course, everything is in biological organism. Everything is done in the language of molecules or bigger molecules, smaller molecules, and so on. Somehow, all these processes are somehow must be governed. You should not have you do not have the specific, for example, morphogen gradient, which is very popular. You do not, what is it, morphogen gradient? It's supposed to be created in this place and supposed to have a sink in the other place. So it should be governed somehow to be done. Of course, everything in biology then translated from the laws into the real situation. We give our signaling, and when we say sensitivity, the last slide, sensitivity depends on the signaling, means we, in the model, in our theoretical work, we put signaling as the information of epigenetic codes of the neighbors. Then this information somehow will be converted in what you say, in this gradient, in these receptors, but it will be governed by genetic information from the neighbors. This is what we try to build in our work, of course.
Thank you. Other questions? If not, then let's thank again. Now is the next talk of Sibelius Khan.
We have 10 minutes break.
Now or 10 minutes?
Maybe I will have 10 minutes break then.
Ничего не
Some coffee in the night. Yes.
А
But I think that the next talk is of Sibelius-Kahn on graph factorization. Please.
I want to thank you to the organizer for organizing such a nice event. It's a pleasure to meet all these experienced mathematicians. And I want to thank you to connecting with the right Sibelius-Kahn because it is the most common name in Turkey, because last name is the most common last name in Turkey. If you search on Google, there is a Olympic weightlifter, woman weightlifter. There's a famous chemistry professor. I'm invited to chemistry conferences more often than I'm invited to math conferences by mistake. All over the world, I always say I'm not the right Sibelius-Kahn, but once I will accept and see what happens. Maybe I should write a paper with her on chemical graph theory or something and write Sibelius-Kahn square. Once I was in the same flight with Sibelius-Kahn to Netherlands. They mixed our tickets in check-in. And once I changed my ID when I lost it and they gave an ID for a completely different Sibelius-Kahn, I checked that no information is correct and things like that. So thanks for connecting the right Sibelius-Kahn. Today I will talk about, it is also originating from some recreational mathematics. I will talk on general results, but at the end I will talk some results, recent results on directed graphs with Uğur, my former student and current student. That's why I also wanted to write their names at the beginning. I also live in the Asian part of Istanbul, so I'm not maybe European, I don't know. But this year I'm in Poland, so I maybe counted Eastern. I will talk about cycle decompositions, then what we mean by factorizations, factors and factorizations, and I'll talk about directed versions and try to show some little bit of constructions of that one. So we know graphs they consist of vertices and edges. We will consider simple graphs, no loops, no multiple edges. So you take a graph. This is an actually kind of simplified version of the definition, and take H to be a subgraph and try to partition the edges into copies of your favorite graph H. This H, it doesn't have to be this isomorphic decomposition. You can decompose the edges into different types of graphs, but I take the simplest version because here we will talk about uniform decompositions. If all your graphs are cycles, then it's called cycle decomposition. For example, take a complete graph, K7, complete graph. In every pair of vertices there is an edge. You can decompose all its edges into one 7 cycle, 1 6 cycle, 1 5, 1 3 cycle. Okay, if you combine all these edges, you'll get a K7.
So what does it mean if all edges can be decomposed into edge disjoint copies of A?
For example, this edge is not used any of other things. It is used only once. Thank you. They are edge disjoint, and their union gives us the complete graph. So we generally talk about complete graphs because it's not an easy question. Since we know the structure well, it is generally.
So what is subgraph H in this example, or any of these subgraphs?
As I said, in this talk I will not talk about such decompositions. For example, in my next example, I will decompose K7 into just C3s, not other things. So everything will be isomorphic to C3. But in general, you can ask or decompose such a question. But since this kind of topics come from also design theory, we generally ask for example, this is a Steiner triple system. So what you think in such decompositions, you, for example, you decompose K7, you think your vertex is coming from Z7. You take a starter, so this is kind of a difference method. S3 cycle. Oops, this is not a good choice. For example, 0, 1, 3. Okay, this will be your starter because the difference of this edge is 1. I can go from 0 to 1 in one step. Difference of this edge from 1 to 3 is 2. Difference of this edge is 3. And in Z7 or K7, all the edges have differences 1, 2, 3, plus and minus. Okay, because if you have such an edge here, 0, 4 doesn't have difference 4, it has difference 3 because you think of the other way, like modular arithmetic. Okay, since it covers all the differences of K7 once, it doesn't repeat differences, I can rotate it clockwise, or more mathematical terms, I can apply a permutation to the vertices, sending 0 to 1, 1 to 2, etc. My next cycle would be 1, 2, 4. Okay, maybe I should have got color show. Excited, I became blind. Okay. This is my next cycle. Again, rotate one more, this is my next cycle. And after 6 rotations, you get 7 cycles, which decomposes edges of K7 completely. This is an example of commonly used difference method. And why is this called Steiner triple system? C3 is actually same as complete graph K3. And in the designs, we try to decompose the sets into some kind of balanced subset, balanced configurations. So our set is this, and we take the blocks as the subsets. 7 subsets here, etc. In such a way that every pair appears in light. Yes. Okay, yeah. Every pair appears in exactly, so if I take 1, 3, it appears in exactly one block. If I take 4, 6, it appears in exactly one block. So in T designs, we have V points, all the blocks have size K, and every T points appear in exactly lambda block. When we talk about Steiner triple system, it is actually a 2 design. So, and lambda is 1. So every pair appears in exactly one block, and K is 3. So this is called the Steiner triple system. And in this case, V is 7. They're also related with codes, their instance structures can be used. Also, in such a case, it is also corresponding to the funnel plane. So I think projective plane can be order Q is the 2 design with Q square plus Q plus 1 points with block size Q plus 1. Okay. So it originated with such block designs, but here we are not decompose them into blocks, so we are not decompose them into complete graphs, but cycles instead. cycle decomposition, alpha yields necessary condition. Number of edges should be total of the edges of the cycles, etc. And each vertex should be in even degree, because each cycle uses degree 2 for this vertex, and combine them, the total degree should be even. And alpha conjecture that this is sufficient for complete graphs, and it is proven by Ryan and Horsley in 2010. But we don't want to just decompose into cycles, we want some other restriction as well. This is decomposition of complete graph on 9 points into again triangles, 3 cycles or K3s. But there is a difference here. You see there are some blocks, there are some chunks. So here we will call them parallel class. Here this is one parallel class, this is another. So we can divide them, all the cycles we can divide them into 4 parallel classes. Here for 7 we cannot do that. But for 9 we can do that. And we want such factors, such decompositions. And later we'll see a K-factor definition. It is a K-regular spanning subgraph. Each parallel class is a 2-factor. The degree is 2, and here it uses all the 9 points of my graph. Here it uses all 9 points of my graphs, etc. And again, it is originated from the Kirkman's question, Kirkman's schoolgirl problem. It was asked for 15 girls. So 15 young girls walk every day, let's say 7 days, and they walk in rows of 3. They say how to arrange them in such rows so that no 2 of them walk twice. Every pair walk with exactly once together. Of course, the order doesn't matter. This girl and this girl, they are not next to each other, but they are in this row exactly once. So actually, this is a solution for 9 girls, because 15 was big. I like drawing for 9s. It's easier. So this is a solution for 9 girls. Over 4 days, one day they walk like this. The next day they walk like this. This will be their rows. These 3 will be together in a row in the 3rd day, etc. And Kirkman triple systems exist. It is shown that for every V3 mod 6. And Steiner triple system exists also 3 or 1 mod 6. There is famous Bose and Skolem construction for this, and actually there is Wilson construction, I think, for that. Again, definition of K-factor is a K-regular spanning subgraph. K-regular, each vertex has degree K. Spanning means it uses every vertex of the graph. For example, in this graph, this subgraph is a 1-factor. Each vertex has degree 1. And it uses all the vertices. This is a 2-factor. And you can see 2 factors is a cycle factor, right? If each degree is 2, it is either a union of disjoint cycles or just one connected cycle, which is a Hamilton cycle. But Hamilton cycle factors are studied a lot because of their optimization. It's famous for the optimization problem, like traveling salesman problem in a weighted graph. So we also consider union of cycles as our 2 factors. So here we talk about 2 factorization problems. Here, these factors doesn't have to be 2 factors. This is a general definition. So again, if we make our decomposition such that these each things can be divided into parallel classes, in other words, factors, it is called a factorization graph. So if each factor has containing cycles, for example, the first factor has R1 many and 1 cycles, second factor has R2 many and 2 cycles, etc. This would be called such factorization. Of course, again, today we'll talk about mostly uniform cycle factors. For example, just dividing this into C5. Not a very sophisticated example, but an example that's easy to draw. So we can, this is one 5-cycle Hamilton cycle factor, this is another Hamilton cycle factor, their combination gives us K5. And as a generalization kind of Kirkman problem, over-Wolfach problem, it is motivated by the seating arrangement in the over-Wolfach meeting and asked by Ringel, it's 1967 or something. So they have round tables in the venue. So you have V participants. For now, let's think V is odd. Because you need, in Kirkman school girl problems, you have 15 girls and you need 7 days. Here again, you need V minus 1 over 2 days, okay, at the venue. You are making the seating arrangement so that at the end of this many days, every participant sits to another participant exactly once together, next to. Not on the same table, but just next to. Direction doesn't matter, it may sit on the right or left, but saying that sits at the end, so you can think of each round table as a cycle. And you can think one day as a parallel class or a 2-factor, because it is union of cycles. When you combine them, you want everybody to sit next to each other exactly once, meaning that at the end, no edge is missing, no edge is repeated once, so at the end you will get a complete graph. So actually, this problem asks 2-factorization of the complete graph KV for odd V. For even V, we will have the degree of the graph, the complete graph, is V minus 1. So when V is odd, since this is even, we can do the factorization. When V is even, this will be odd. But again, they pose the variation of the problem. They said first remove a 1 factor from the graph. So remove 1 degree from each vertex. And decompose the rest into 2 factors. This is also called over-Wolfach problem. And this is called sparse avoiding version. Why? Because at the end of V minus 1 over 2 nights, you sit next to each other exactly once, except one person, because a 1 factor is removed. If you are this person, you don't sit with that one because this is removed. They say if you see your spouse every day in the conference, you don't want to sit next to them. So it's called spouse avoiding version. And again, in the original question, these table sizes may differ, but it would be a very difficult question. And the assumed version and most studied version is accepting all these table sizes are the same. Okay. For example, here it is not uniform version. For example, you have tables, very small meeting with 7 people, and on 3 nights, you have table with 3 people, table with 4 people. At the end of 3 nights, if you combine them together, you get K7. Okay. What is done so far? Some non-existent results are shown for some configuration problems. And single cycle size is mostly done. And various cycle sizes, but the vertex number is less than or equal to 40 is also worked on. And bipartite factorizations, when all cycle sizes are even, are also solved. Actually, there is a recent asymptotic result saying that If vertex number is large enough, if this happens, if that happens, if cycle size is large enough, you expect to have solution for everything. So expected result is everything will be solved, but this asymptotic result doesn't give, it is probabilistic and doesn't give insight on some construction method. It is good result, but we like to see some nice types of constructions and for specific number of vertices. One extension of the problem is Hamilton-Waterloo problem. Here's the Hamilton is not related with the Hamilton cycle, it's not related with the mathematician, Rose Hamilton. It is related with the location in Canada. Waterloo is also in Canada. This problem is posed by Alexander Rosa, who was at that time McMaster University in Hamilton, and I think Charlie Colburn was in Waterloo. They say, what if our venue is not in one place, but in two universities in Ontario, and one venue is in Hamilton, one night you stay in Waterloo? What kind of thing may happen? So in the overall fun problem, you have one type of two factors, and you decompose everything as two factors isomorphic to that. So now you have two types of two factors, and you decompose your graph to two factors such that each factor is either isomorphic to this or isomorphic to that. Okay. Again, the uniform cycle sizes. Let's say this factor consists of only m cycles. This factor consists of only n cycles. Is studied. It is denoted by HWP, either talking about cycle sizes at the beginning or writing the factors on top. Here R and S means R of the factors isomorphic to F1, S of the factors are isomorphic to F2. What would happen at the end? It will be total number of factors. Okay. It's also denoted by URD, uniformly resolvable decomposition. It is a general description. It helps you to add more than Hamilton-Waterloo have two factors that are not isomorphic. You can have uniformly resolvable decomposition adding a third factor, fourth factor, etc. It's also called generalized overall problem. Adams, Billington, Bryan, Zanatti, they gave the first necessary results. Of course, it's obvious. If you have a factor of m cycles, m should divide the number of vertices. If you have n cycles, it should divide the number of vertices, and total number of factors. For example, what do we say here? You have 12 people. This is positive avoiding. You are left with one factor. And you have 5 nights. And in 2 of the nights, you sit in Hamilton where you have tables of size 3. In 3 of the nights, you sit in Waterloo, you have tables of size 4. What is to solve Hamilton-Waterloo problem for so this is a specific solution for R equals to 2, S is equals to 3 for 3 and 4 cycles. But having a complete solution to Hamilton-Waterloo means that all possible configurations of R and S that gives you this sum. If you find the decomposition map, R is 0, S is something, which is also an overall problem. R is 1, S is V minus 1 over 2 minus 1 is Also, on Aristo, it is blah blah. So if you find a solution for all possible configurations, you say, okay, I have a solution for this one. That's why specific cycle sizes are hard. I also drew it like this. These are the 3 cycles. These are the 4 cycles. So first works also on specific cycle sizes. I'm working on even cycle sizes are always easier because of some symmetry conditions. And Horak in 2004, Deniz and Link 2009, and Bryant in 2010, they talk about Horak and Deniz and Link, they talk about triangle factors and Hamilton cycle factors. Bryant, Danziger, they solved for bipartite 2 factors, meaning that even cycles, but many exceptions. 4 cycles and M cycles when M is even solved by Hu and Huang. And when I was in Michigan Tech with Melissa Kern and I solved a 4 cycle and an M cycle for any M odd when I think R is 1. Yeah, single factor of M cycle and rest is 4 cycle. Because when we start working on that, we asked Danziger Bryant, who worked on this problem a lot, where can we start? Most of the exceptions, I didn't write the exceptions in all the results, are if one factor is like when R is 1 or when S is 1, is mostly an exception. So they say we couldn't get results. In this case, one factor is different and the rest is like overfold path. So we started doing that for 4 and M cycles. Actually, our construction also works for the even cycles, but we realized it is solved before. And with my former student, we complete the rest of the cases. And we also, NM, this should be MN for M. Sorry, I wrote it wrong, otherwise it won't be a different result. In 2017. And lately, it is almost completely solved because there is a team, Burgess Danziger from Canada, Tretta from Italy. They attacked this problem. Actually, they used kind of something I'll show later, this lexicographic product we did with 2, but they generalized it to analyze the cases where M and N both odd, because both even are studied before as bipartite factors. And when they have distinct parity, it is even more difficult. When one cycle is even size, one cycle is odd size. Okay, so they attacked, and now they have a new paper in archive, because in those cases there are lots of exceptions. And they almost filled those exceptions with their 2022 latest paper. Again, there's an exception of the exceptions, but for example, when V is M times N, it is multiple of the cycle sizes. It is still an exception. You would think this is the easiest case, right? Because the bigger cases are solved easily, but when you go down to the smaller cases, it is actually, it gets difficult, like projected things. So directed versions are also studied. In the directed version, you are not working on the tournament graph, but you are working on the symmetric complete graph. So between each pair of vertices, you have both arcs in both directions. So at the end, you sit once on the left of someone, once in the right of someone. So now we have the direction. And it is not like OP star and HWP star. And your cycles are directed. Now, they don't have both sides. The cycles are directed, but the graph you decompose is the symmetric graph. And there's no sparse avoiding version of this problem because you don't need, because you always have even degree right now. So also, if you make a decomposition of this into directed cycles, then you remove directions. Actually, you get a decomposition of two-fold complete graph into given cycles. But the opposite is not true. Okay? For example, you have a decomposition of two-fold complete graph K4 into 4 cycles, but you cannot decompose symmetric complete graph into directed 4 cycles. Similarly, other examples. Okay. So it is solved. Some cases with fixed cycles lengths are solved very earlier, 3 and 4. And again, there is a huge break because between those time undirected cases were attacked. And Burgess and Sajna have latest paper when M and V are both odd. And I think they have some paper on archive now which is not published, which has more results on that. And this is also Sajna and Shabani. In the overall problem now you have not a uniform factor, but you have one CM cycle like 3 and 4 and one bigger cycle factorization. But no Hamilton-Waterloo yet, and we talked about the necessary conditions similar to the undirected case, but the number of factors is not v minus 1 over 2, it is v minus 1 now. And again, similarly to what is done in undirected cases, we first attacked the even cases, small even cycle sizes. Also, again, small parity, both odd cycle sizes, and we succeed to solve them. And one good observation, now, since the degree is more, we have twice more number of factors, so we have lots of configurations we need to think about. But luckily, we can use the undirected case when R and S, even in the directed case, they come from the undirected version. So we need to look at the odd number R and S. Okay? Because you can take 2 copies. Again, if G is a graph and H be a subgraph, if G has an H factorization, then G star has a H star factorization. And Burgess and Sajna also gave factorization of bipartite complete graphs into direct CM factorization, which we will use as a tool. And there was a nice result of Liu, which is used as a tool in many other factorizations on, again, complete multipartite graphs with y parts, and each part has size y. So in the complete multipartite graphs, okay, you have y parts, and each part you have x vertices. Inside of each group, no edges. All the edges are between the groups. Okay, this is complete multipartite graph. And Liu has solved the overall problem for the complete multipartite graphs with giving some non-exceptions. We also use this result. Actually, I use this notation as the union in the same vertex set. And when we say the difference, it is just removing the edges, not the vertices. Alpha G means the alpha copies of the same graph. And we also defined, it's not our definition, the read product is defined also with undirected graphs, but the directed will replace the edges with arcs. So G read H means that You replace each vertex of G with a copy of H. We rename it as Hx, and each arc of x, y in G is an arc pointing of each vertex from H x copied to the y copy of H. Okay. For example, let's take our G like this and H like that. So in G, for each vertex right now we have H. And since there is only one H here, it means that put an H arc between every vertex of this copy of H and this copy of H. We generally use for H some empty vertices, like complement of E. For example, if you take a C, let's say C4, we generally take the two copies for our purposes, but you can generalize it. So we take at the end, there's an edge between these two. I'm showing the undirected case. So there's an edge between, this is x0, let's say y0, this will be x1, y1. If in my original graph there is an edge between x and y, there will be an edge between the copies of x and y. So there is an edge between these two, edge between these two, and there is an edge between these two. So it is not complete graph inside. It depends on the edges of your original graph. If you take a complete graph and take this, it would be a complete multipartite graph. Also, KD, thinking some graphs as KD graphs helps. If you want undirected copy, you want your difference set, the S, as inverse closed. You want inverse of the elements. But since we are working on directed ones, you don't need the inverse of the elements in your difference set. For example, in Z9, let's use difference 1, negative 1 in this case. And difference 2 would be displayed edges. In our proofs, we will denote some things like that. For example, we take the directed copy of Cm, take the product K2, and we show that this can be Cm factorization, factorized into Cm, directed Cm's, or directed C2M's. Again, we denote the vertices of this product Z2 cross Zm with the connection set 0, 1, 1, 1. I think 0, 1 makes the side edges and the other one makes the inside edges. And for our first cycle, we take our vertices of this cycle to be 0, I. So for example, in the 0th level, we take this cycle. Then we add 1 0 to that. It means that take also this cycle when you add 1 0. Okay. And when you combine them, you get one factor. And these mixed edges will give you cycles used the inside edges. Okay. For example, let's go to the example. Take the product of C6 directed with K2 complement with empty graph. So you get this graph. The one we defined gives our first factor as the side cycles and this cycle. Okay. Again, we add, for example, here you see that these same level edges are missing because we don't have loops here in the cycles. When we add these edges at this one factor, we can factorize it into 1 Cm to Cm cycles. Similarly, now our connection set is different. Okay. And similarly, we decompose it to that. This is decomposition because we mostly use recursive constructions. When you have a bigger graph, you decompose it onto smaller graphs first, then you fill the smaller graphs with your previous decompositions and combine them together. For example, kx star read product. Sometimes this read product is half its construction. Instead of saying this read product, I think it can be said that the second power is taken. It's written like this. K star, K2 star factorization. It also, if you take the read product with K2 star, it actually gives you a complete graph on 2x vertices, symmetric, minus a one factor removed, because again the same level edges are not included. And we know that from Kotsik, K2x has a one factorization. If K2x is a one factorization, if you remove one factor from K2x, the remaining thing will have also one factorization. So just use this to get the double edges. Our main construction tells that if you have Hamilton-Waterloo problem on solution, the same cycle sizes on H vertices, then you get a solution for a multiple of H vertices. This is the recursion step. The reason is, if you take a complete graph, symmetric or not symmetric, undirected, doesn't matter. You can think this on H times X factor. You can think them as X copies of KH. And the next one, read product, gives us the edges in between. Okay. So if we have a solution for the KX, we also combine it with the overall fast solutions with the multipartite graphs and get the desired numbers. So of course you need to be careful on that. For example, if you have a solution for 8 and 12, these are the small solutions we got through some computer search, or some of them nice constructions, some of them are computer search. And for also 16, for example, some cases have nice construction. You decompose case 16, for example, into 8 cycles, and you can think this K8 cross K2 complement, and K8 has Hamilton cycle factorization, and plus you have one factor. You take some of them, however many you need, and you already, in our lemmas, there's factorizations for that. And we also gave another lemma to describe factorization. When one factor added, the idea is combining them. Okay. Again, for odd and we use similar things, but we think each KH actually some tripartite thing. It's not as easy as even ones, and we use its main construction. And again, for this one, since their list 3 and 5, 3, 15, 5, 15, their list common divisor is 15. The base block would be 15, having solution for 15 for all these cases. Together with solution will give you 15 times x, which the vertex number according to the necessary conditions is given. Okay. So if V 15 divides V, this previous solution gives rise to that solution because of the recursive construction. And this is the combination of results. We have more results, and this year I'm in Poland. I started working with Mariusz Meszka. I talked about some general solutions because we start to get an idea with the small numbers. We sent those to publishment, and we have more things to publish soon. And he thinks that, oh, give me a weekend, I'll get you some solutions to that. And now after 2-3 months, he accepted that, no, this is a difficult question, I couldn't get any idea on that. Because we don't don't want to repeat the same types of constructions and with different numbers. You want to get some general idea on this. So this year I will, among other things, work on that. This is some type of intersection of designs and graphs. I also work on structural graph theory, some dominations on KD graphs and some equimatchable graphs where all maximal matchings have the same size, if you're interested in. And this is the real Sveroskan's email. If you want to contact, I want to thank you for listening.
Okay, let's stay.
Remark? If not, then let's stay together.
Now we have a coffee break. And we enjoy the coffee break outside.
here.
Okay, so we're tired, but there are still two interesting talks. The first talk in the last session today by Professor Stefka Bulgaria from Велико Търново University. It's titled Linear Codes of Tonality and Automorphisms. So some classical theme in this area.
Thank you.
Stefka, please.
Thank you. First of all, I would like to thank the organizers for inviting me to present a talk here. Actually, I have been involved in different events about women in mathematics during the years. So that's why I decided to prepare talk with two sections. The first section is a popular one. It is about a project. Sofia told something about it, but I also prepared a few slides about this project. And the second section will be the scientific section about the research I am doing.
The first one is also scientific, right?
Yes, but there are many pictures in this part. This is actually the exhibition, Gallery of Portraits of Women in Mathematics. And in the beginning it was actually 13 such posters. I was invited to participate in this project, and one of these posters is mine. And actually this exhibition traveled all around the world, and I had interesting experiences about this exhibition. For example, I received letters from colleagues from different countries, for example from Brasilia, writing me that they saw my poster somewhere there, and it was very interesting, and they made pictures with my posters talking to me. That's why I decided to tell you some words about this exhibition and this project. And it is not only an exhibition, it is there is also a booklet here. This is the first version of these books, because here in my book I have only 13 pictures, actually not pictures, but there are also interviews with 13 women mathematicians from Europe, but the second edition of this book is this one with 20 women mathematicians, including Sofia from Greece. And this is the cover and the back, actually the front and the back cover of this booklet. Here, and one more interesting thing, this is a front cover. This is a picture of blackboard in Veliko Târgu University. And I think the photographer liked this picture because this blackboard is not very clean. And you see some parts of what was written here, and some parts how we tried to clean the blackboard, etc. But this project was a very interesting experience for me. Here, actually, I have many interesting pictures. You see here, this is from Beirut, this picture, and this is one of the posters. But in the book here, you see these young women. They read my interview here. This exhibition traveled a lot, and the starting point was in Berlin, and I went there for this opening. It was in the European Congress of Mathematics 2016. I have also interesting pictures from there, but no time for so many pictures to present here. But here I list some of the places where this exhibition was given. In many places, not only in Europe, but you see here in Japan, in India. I don't know about Bulgaria. Actually, I have a copy of this exhibition, and I myself showed in Kazanluk, for example, posters, but not original posters actually. There are similar projects in different countries. This booklet is about Australian women in mathematics. I know about different, for example, in various countries in Mediterranean, maybe in Slovenia or Slovakia, you said that women organized somewhere.
In Slovenia, they just said because they organized the 8th ECM, they said we should extend to Mediterranean countries. That's how they expanded from 13 to 20 portraits. Yeah, that's all. So
I see.
Yeah.
And this is the main coordinator and creator of this project, Sylvie Paicha, and I decided to put her picture here because I think maybe it will be good. It will be good if you invite her next year. She is not from Southeastern Europe, but she is very much involved in this movement, Women in Mathematics, and also she is a good mathematician, Sylvie Paicha. I don't know if somebody of you know her, but she travels a lot, attending many conferences, and because of her, this exhibition travels all around the world. Okay, and this is me telling about linear codes and orthogonality on the blackboard in Veliko Trnovo University. Actually, Sylvie and the photographer, all these pictures were made by a professional photographer, and actually they came to Veliko Trnovo to make these pictures, these photos of me, and I felt like a star, like a model. Then, and and I will speak here about linear codes to you too. Okay, this is the scientific part of my talk about linear codes, and I will begin with some well-known definitions. Some of the colleagues here know these definitions, but not all of you. That's why I decided to give these definitions here. Very important in this area are the finite fields. Fq by Fq, we denote the finite field with Q elements, and Q, of course, is a prime power. And this is the n-dimensional vector space over this finite field. We need here matrix, so we define the weight of a vector in this vector space to be the number of non-zero coordinates of this vector. This is called also Hamming weight. We use also Hamming distance, but actually for linear codes we don't need this distance, we need the weights. And linear NKD code, or linear code with length n, dimension k, and minimum distance or minimum weight d over the finite field with q elements actually is a k-dimensional subspace of the considered vector space, and this d is the minimum among all non-zero weights of the vectors in the code. The vectors are code words. Okay, and what we need some more, our linear codes are represented by their generator matrix. Generator matrix is K times K by M matrix, whose rows are form a basis of this linear subspace. Let's say something about orthogonality conditions. If we define an inner product in our vector space, in the considered vector space, we can use the orthogonal complement of our linear code C, and this orthogonal complement is called also orthogonal or dual code of the code C, and it is also linear code of the same length n, but the dimension is n minus k. We don't know about the minimum distance before in advance, and what we need here is the intersection between the code and its orthogonal complement. This is called the hull of the code C, and depending on the dimension of this hull, we define three different types of codes. LCD codes, these are codes in which the hull has dimension 0. This code consists only of the zero vector. Actually, this is the situation when we have linear spaces over the infinite fields, like real linear spaces or complex linear spaces. But in the case when we have linear spaces over finite fields, we can have also different situations. For example, the code C to be subset of its orthogonal complement, And so the hull is coincides with the chord, then we call this chord self-orthogonal. And if the chord coincides with its orthogonal complement, the chord is called self-dual. And self-dual chords are studied for have been studied for long years, because actually these chords appears relatively rare, and that's why they are more interesting for researchers. And also many of the chords which are used in applications are of this type, self-orthogonal or self-dual chords. Self-dual chords actually exist only for even lengths, and the dimension of these chords must be half of their lengths. Self-orthogonal chords may exist for all lengths, and the dimension are less or equal to half of the length. But LCD chords, they exist for many lengths and dimensions. I wanted to say for all possible lengths and dimensions for which linear chords exist, but I'm not sure in this statement. So I have to think more about. But actually, if we fix the length and the dimension, and we know that there are such LCD chords, then I have some research on this. How many of the chords of this length and dimension are of the type LCD, which means the hull has dimension 0. How many chords have the hull with dimension 1, dimension 2, dimension 3, etc. And actually, LCD chords, the number of LCD chords is the larger number.
Excuse me, what did you say is the length of the chord? What was the length?
The length, actually the chord consists of vectors, dimension of the space, yes. This is the length of the vectors in this chord. We consider so-called block chords. All vectors have the same length in this chord. Okay. Actually, if we consider orthogonal complement of these chords, we need to know what inner product to choose. And this more common, we use Euclidean inner product or Hermitian inner product. Euclidean inner product is the usual inner product we consider in real linear spaces. The Hermitian inner product over finite field Q element is defined only if Q is an even power of prime P, and this is the definition here. And this Hermitian inner product is similar to inner product we consider in complex linear spaces over the complex complex field. In the binary, this is the most common studied chords, called binary chords. These are chords over finite field with 2 elements only, and in this case we have only Euclidean inner product. Ternary chords, chords over field with 3 elements, again on Euclidean inner product. And quaternary, in the quaternary case we consider both inner products, and so we have Hermitian chords and Euclidean chords. Euclidean chords. Using this inner product, we can consider self-orthogonal, self-dual, LCD chords, depending on the inner products. Next thing I need here is the equivalence of chords. And I give 2 definitions for equivalence here. These 2 definitions actually are similar. The definitions are equivalent to each other, which means that from the first definition the second follows, and vice versa. We say that 2 linear chords with the same length and the same dimension are equivalent, over the same field of course, are equivalent if one can be obtained from the other by a sequence of distant 3 transformations, a permutation of the coordinate positions, multiplication of one coordinate in all chord words with a non-zero element of the field, and also a permutation of the field. And the sequence of this transformation, which that maps the code C to itself, is called an automorphism of the code C, and the set of automorphisms form the automorphism group of the codes. But in some of the in the proofs, we need another definition, a more, how to say, more structural definition for equivalence. And this is the second definition in which we use matrices here. Two codes of the same length and dimension over the finite field FQ are equivalent, provided there is a monomial matrix M and also a field automorphism gamma, such that the second code can be obtained in this way. This means that if we multiply the code word from C1 by this matrix and apply the field automorphism flow coordinates, we will have a code word in the second code. Monomial matrix is a product of a permutation matrix and a diagonal matrix with elements of the considered field. If we have a prime field, which means if Q is a prime, then this automorphism group of the field is trivial. Okay, and what we know, what we can say more about LCD codes, these codes that the codes and its orthogonal complements don't have common code words instead of the zero code word. The first theorem is proven first by James Macy, 1992. It is interesting that actually these LCD codes are studied from this year because they are somehow natural. Because we can compare them with linear subspaces of a real vector space or a complex vector space, but somehow they had no applications before this year. And Macy proved that if the matrix G generates a linear code of length n and dimension k, then this code C is Euclidean, respectively Hermitian LCD code, if and only if this matrix G multiplied by the transpose of G is a non-singular matrix. In the case of Hermitian inner product, we use the conjugate and transpose matrix of G. Actually, we have similar theorem for self-orthogonal codes, and for self-orthogonal codes we can say if and only the code is self-orthogonal if and only if this product here is equal to the zero matrix. But there is an interesting theorem proven recently by these mathematicians that any linear code over the finite field with Q element, if Q is greater than 3, is equivalent to an Euclidean LCD code, and any linear code over FQ square for Q greater than 2 is equivalent to an Hermitian LCD code, which means that if we take a linear code over a field with 5 elements, for example, this linear code is equivalent to an LCD. And if we take an Hermitian linear code over a field with 8 elements, for example, it will be equivalent to an Hermitian LCD code over the same field. Which means that actually it is not a very interesting question to consider LCD code over bigger finite fields, because it is the same if we consider linear codes, simply linear codes. That's why the question for existence and classification of LCD codes is interesting for codes over fields with 2 elements, with 3 elements, and Hermitian codes over fields with 4 elements. Okay, and for constructions and classifications, we can use the automorphism group of the codes. Here I give some more details about these automorphism groups. If C is a linear code of length n over a finite field with q elements, then we can consider three different automorphism groups of these codes, depending on the fields also. If we take only the permutations that are automorphism, which means the permutations that fixes the code, the considered code, then we will have the permutation automorphism of the group of these codes. If we take all monomial matrices that map the code C to itself, then we have the monomial automorphism group, and in last we have the full automorphism group of the code, which we can denote by odd C only, or in some cases gamma odd C is used also. But if we have a prime field here, then monomial automorphism group actually is the full automorphism group of the code, and if we have a binary code, then the automorphism group actually is a permutation automorphism group, and we can consider these automorphisms as permutations. Here I give the same details with the matrices, and there is a very useful lemma proven by Kari Kaufman many years ago, that if C is a linear code over a finite field with q elements, with an automorphism denoted here by T of prime order, and we have these conditions from this prime order R, then there exists a code C equivalent to C prime equivalent to C, where which has an automorphism of the same prime order, but which is a permutation. Which this lemma allows us to consider only permutation automorphisms for the codes that we consider, which is very convenient for us to consider only permutations. And that's why we focus on the permutation automorphisms. And as you know, we can consider this permutation automorphism as permutations represented as a product of independent cycles. And here, sigma is our permutation, and this sigma is product of these cycles. This is a permutation of length R, further R, which is decomposed into factorized into C cycles of length R and F cycles, F fixed points, F cycles of length 1. And using this structure of the permutation, actually we can define two subcodes which are important for us. The first subcode, F, which we denote by F, consists of all code words which sigma preserves. And the second subcode consists of all code words with this condition, which means that if we summarize all coordinates in one cycle, we have 0 in the considered field, of course. And our code C is a direct sum of these subcodes, which is also very important. And also these two subcodes are sigma invariant. The second part is very easy to prove. The first part is more difficult, but this theorem proven by Huffman is also important in the consideration of the structure of these codes. And actually we can decompose in more details the code C, and here if we consider the structure of this polynomial, we consider an automorphism of order R, and we need this polynomial here, x of power R minus 1, and its decomposition, its factorization into irreducible factors. And if these are the irreducible factors of this polynomial over our finite fields with q elements, then we consider the factor ring. Where is the factor ring? This is the factor ring here. The ring of all polynomial in one variable x factorized by this ideal, principal ideal, generalized by this polynomial here. This factor ring is a direct sum of fields which is important from us. And we then, using these fields, we can decompose the second subcode, which we consider, into linear codes over these fields. So we have here linear codes over these different fields. And then the code C can be represented as a direct sum of these linear codes, as these codes are linear codes over different fields. This is interesting here. Okay, let's focus on the binary case, because actually binary self-dual, LCD, and etc. codes are more interesting for me in my research, and also are more usable for different applications. And we consider automorphism of order R, and these are the irreducible factors. And here, this is the general case when these factors are of different lengths, and R is the least common multiple of these different lengths. Then we can decompose our code C in the same way, as a direct sum of subcodes, called fixed subcode of all vectors which sigma preserves, and the second one we call the second subcode the even one, because actually if we take the restriction of any code word on each cycle, this restriction has even weights, which means even number of ones in each cycle, and the code C is a direct sum of these subcodes, and moreover, these two subcodes are orthogonal to each other. Okay, and what we have for these subcodes, if we consider R the order of this permutation to be an odd integer, then we have this theorem for the fixed subcodes. If we take the fixed subcode of the code C and the fixed subcode of its orthogonal complement, then we have, I forgot to say that we use here a projection map, because actually in this fixed subcode, in any cycles, all code words have the same coordinates. That's why we can use the projection, and the projection of this subtraction here actually is equal to the projection of the code C and the projection of the code its orthogonal complement, and this is actually the hull of the projection code. And this theorem is very helpful. Actually, this theorem is from my last work, which is published this year, 2022. And we have a very interesting corollary here, that if C is self-orthogonal code, that this the projection of its fixed subcode is also self-orthogonal. If C is self-dual, this projection is also self-dual. And if it's an LCD code, this projection is also LCD. And what is helpful for us with this projection is that actually this projection code, it is again linear code, but with smaller length, with smaller dimension. And if you want to construct codes with bigger length and dimension, we can use already obtained results for smaller codes. The situation is with the second subcode we consider, the even subcode, is much more complicated because we can consider the structure of this code, but we don't have a projection map here. We use something different to the restriction of any code word of the cycles of length. Here, I present the theory for odd prime because it is a little bit easier to consider odd primes for the order of the considered automorphisms. If we take this restriction, we suppose to this restriction we map this vector to a polynomial in a natural way, and we consider then vectors, the vectors in the even subcode as vector of polynomials. These polynomials actually can be considered as polynomials from this factoring, and actually not only for this factoring, but as they are even weight polynomials, we consider them as polynomials from this P. P is actually a module over our considered field. And we need to know what is the structure of the, not only on the even subcode, of the image of this even subcode, if we map any restriction of the code words here on the corresponding cycles to polynomials. What happens with this image? We call it C5. What is the structure of this image? To know the structure of this image, we need to know the structure of this factoring. And the structure of this factoring also as in the previous case I showed here, depends on this polynomial, x of power p minus 1, and how we can factorize this polynomial over in this case, the binary field. And if this polynomial is factorized only in two factors, x minus 1, and this is the second factor, and this second factor is irreducible over these binary fields, then this module of even weight polynomials is a field with 2 of power p minus 1 over 2 elements. This is the easier case when we have here a field. And then this code C5 is a linear code over this field. And we have here similar theorem to the theorem for the projection code. If C is a binary linear code, invariant under the permutation sigma, then this code C5 is also self-orthogonal code, but over this field pi. And also with respect to this inner product here, defined here. The inner product is different. If C is self-dual, C5 is also self-dual, and if C is an LCD code, C5 is also LCD, but with respect to this inner product and over the field P. And if P is not a field, which means that this polynomial x of power p minus 1 has more irreducible factors, then pi actually is a direct sum of different fields. And what we use here is also that in this factorization, the irreducible factors, some of the irreducible factors are self-reciprocal polynomials, but the others are divided in pairs. The polynomial and its reciprocal polynomial. So then this module pi is a direct sum of these linear codes over, actually these are not linear codes, these are fields, and the code we consider C5 is a direct sum of this type of linear codes over these different fields. And we have here, you see, more complicated structure of these codes. And also we have here more complicated conditions from these codes if we want codes the code C to be self-orthogonal or self-dual or LCD codes. So we have this color is here for the codes in the case for this linear codes over this more complicated fields that we can use. I have here one example, but I don't have to explain it in details. So I will go to my last slides. Actually, I decided to show you here that I work on this research for many years, and in the beginning, in my research I considered preferably self-dual codes, and work in the beginning with colleagues in Bulgaria. My PhD advisor was Vasil Yorgov, I didn't mention him here, and then with different authors we considered self-dual, self-orthogonal, and LCD codes recently with different structure, with automorphism of prime order or composite order. And that's all. Thank you very much.
Thank you. Some questions or comments?
I'm an outsider, but I should like to ask you if you also have some characterization results in the sense if and only if, because for instance the last theorems I noticed that
Here, for example.
Northema theorem.
The next.
Yeah.
Here.
Then.
So if
no, I don't have here if and only if because actually I consider only a part of the code here.
Okay.
Because we have two subcodes, and if there are theorems if and only if, but we can consider combine. Where is the? No, I missed some. We can combine this one here for this projection code CPI and this one. And then I have with if and only if, but I decided not to show because too many things.
Thank you very much.
But if you combine all parts, is it?
What do you mean?
Okay, you consider part of the code and you can.
But the code
say
is a
something.
direct sum of this subcode.
Yes.
So if I have something proven for the first subcode and something for the second subcode, then I can
all
have
individual.
if and only if
Yeah.
for both.
This should balance.
It's interesting. Thank you.
Okay. Yeah. There's some other questions, comments?
Can you mention some of the applications to cryptography or?
Actually, there are applications to cryptography, especially these LCD codes are considered recently, are studied recently because of the implication, the applications in cryptography. But actually, I cannot say about this application now. I have to study more to say about these applications. Because actually my research is on codes, not in cryptography.
You may know secret sharing schemes, yes.
Is the first application IMSA.
This
By
should be from
Messi, yes,
60s.
Recently channel attacks, resistant to channel attacks.
So you work against the cryptography because you classify them and then.
And I only in the introduction of my papers I write there are these and these applications, but actually I didn't read about these applications.
Yeah, so all of us need motivation to say why this is important. Sometimes we don't know how it's important. Okay, I don't remember actually. I didn't. Did you say that? Actually, I suggested Sevka to start with LCD codes, and maybe because I saw some applications, and I know that she is prepared in this field. So, it looks like she did quite well for a few years.
Thank you. Thank you. I had to thank you also to show me this research on LCD codes.
This is often it's necessary to give the right problem to the right person. Yeah. Okay. Some other questions or comments? Oh, I don't see. So let us end again. We have 6 or 7 minutes. What Let us start with the last talk of this session and today. The last talk will be given by Oksana Kravchenko. She is originally from Kharkov University of Radio Engineering. Also, I like she is with our institute since that unfortunate war, and fortunately we were able to offer her position, and she will present some results from her dissertation.
Of the doctors.
Yeah, this is in Ukraine, like in Bulgarian, they have second stage of dissertation, so-called large dissertation. So this will be
Like habilitation.
Something similar, yeah.
Excuse me, my English is not very well, but I learn. I will read. I do researches in signal processing, radio engineering, and telecommunication. All these sciences are based on mathematical method. Electrical circuits are described by equation, system are described by linear and non-linear differential equations. Also, the signal always carries information. The signal reception has the noise. Noise presents an interference. That's why statistical method takes big place in those sciences. Slide 2. Slide 2 shows types of interference. The main and the most difficult problem of the signal receiving is the problems of noise immunity. The problems of finding the best method for radio signal receiving with the noise presence is one of the main goals in radio engineering and telecommunication. I want something about also there are the problem of finding the best method for radio signal receiving with the noise presence is one of the main goals in radio engineering and telecommunication. Also, there are space noise which aren't presented on this slide. White Gaussian noise is a raw noise model in radio electronics because, as you can see, there are many difficult noise and interference. What equates to central limit theorem. You know about this theorem, your mathematics. Next slide. Main noise reduction methods are listed in slide. All of these methods are described with help of mathematics. Errors, correcting codes, lecture, как передо мной. Before me, told about correcting the codes. Let us to detect these codes. Let us to detect any mistake, and some of them even to correct it. Optimal filter out signal has maximum signal to noise ratio, but the signal shape does not save. For example, filters are not only devices. Some of the filters are mathematical formulas. With the usage of coherent assimilation detection method, the signals stack coherently. Digital signals are created for noise reduction. Digital signals are convey information with less noise, distortion, and interference. Next slide. It's a concept of stochastic resonance. The researchers made in 1980s brought us to paradoxical conclusion. The stochastic resonance effect characterized the nonlinear system responsible for the weak input signal. Nonlinear system parameters such as the gain and signal-to-noise ratio have its maximum in the specific condition. Nowadays, this effect is fundamental. The stochastic resonance concept was introduced by physics researchers of the Ice Age. Stochastic resonance takes place in various sciences, in biology, physics, chemistry, medicine, sociology, etc. For example, with little noise present, the human can hear even better than without it. At the same situation with the vision. When a photo has a little noise, we can see more clear. Stochastic resonance is based on the idea that with the noise help, the useful signal in nonlinear system could be amplified. Let's consider Let's consider the particle in symmetric with stable potential. The particle is under weak periodic signal. The particle moves. The particle moves up and down and cannot jump over the barrier, But if the noise would be added, the particle would jump over the barrier. The frequency of the barrier crossing will be equal to the periodic signal frequency at the certain noise level. It's a It's of stochastic resonance. Slide, next slide. Next slide. The motion of the particle is described in slide, where x particle coordinate, x0 minimum points, and barrier delta u. Stochastic resonance described by these equations. Noise, harmonic signal, this input signal, X output signal. This equation is Abel equation of the first kind and does not have an analytical solution, unfortunately. It is also impossible to find the two-dimensional probability density of the output signal, meaning of the exact solution of the Fokker-Planck equation, even in the absence of external harmonic signal. Consequently, the correlation function and the spectral density of the output signal are not exactly determined. Naturally, with the inclusion of the periodic external force, additional difficulties arise in the analytical description. What nonlinear system with stochastic resonance effect. Input signal plus noise is output signal. For example, numerical simulation of output signal of the system driven by additive mix of harmonic signal and white noise input is shown in figure. black line is harmonic signal. The blue line is the signal noise mixture, and the output signal line is red. You can see the significant noise reduced on the nonlinear system output. Spectra of the output and input signal. First input, second output. You can see noise, level of noise not increase. Output noise pulse is reduced, you can see. Signal to noise ratio is very important characteristic of the system in radio electronics and telecommunication. Fig shows us output signal to noise ratio dependent on the noise dispersion. You can see maximum, local maximum at d equal 0.4. This point is the Hesser point, stochastic resonance point. Anti-resonance, you can see anti-resonance point in any paper describe this. Anti-resonance point at the minimum point on the graph. D equals 0.2. Stochastic, and next slide, stochastic resonator output signal to noise ratio depend on the input harmonic signal frequency. Вот. For input signal to noise ratio. Result of calculation are given in figure. The figure shows that the phenomenon of stochastic resonance is expressed better at low frequencies. So a nonlinear device having the effect of stochastic resonance is the low pass filter. In addition, there are a minimal output SNR signal to noise ratio at the frequency 0.2. As this effect is observed at the inputs signal to noise ratio. Output signal to noise ratio is a nonlinear function of the external noise and the input harmonic signal, as you can see. Something about radio engineering. The theory of linear system is highly developed in radio engineering. Linear systems are characterized by transfer function and pulse responsible. If spectrum of the input signal is known, it's easily possible to find the spectrum of output signal. And if you know the voltage in the input signal, you can find the voltage of the output signal. very easy, is very beautiful theory. But when system is non-linear, in the nonlinear system analysis, it is somewhat difficult to obtain exact formulas for the output signal. The always method with transfer function usage gives us a big perspective. The vector series are widely employed to present the input-output ratio nonlinear system. This representation is based on the Volterra transfer function. The Volterra series is the type of functional series which connects the system input to system output, as you can see on this slide. Y is the output, X is the input, E can, G N. Analysis of the system nonlinear component is based on the multi-dimensional Fourier transform, also known as the Volterra transfer function. The n-fold Fourier transform is described by this formula. The one-fold Fourier transform is the linear system transfer function. To calculate the transfer function, we use the harmonic input method. This method is based on the fact that a harmonic input must provide a harmonic output. The nonlinear different equation, such equation, is described in the paper. This paper. The output properties of Volterra system driven by harmonic and Gaussian input, bounded by Bressian and Rice. Rice is also known for the Rice distribution. The Volterra transfer function we receive for the this уравнение, for this equation, or such formula for Volterra transfer function for equation stochastic resonance. Three cases are under consideration: harmonic input, Gaussian noise input, and sine wave plus Gaussian noise input. If there are no noise, the input signal can be described of this formula. If we solve the stochastic resonance equation for this case, the leading terms of the output signal are given here. Output signal equal such formula. Let's determine the power spectral density of the output signal. The power of the first and the third harmonic are given in table. In radio engineering is very important signal spectral analysis, very important. In each paper, radio engineering have spectral analysis. Такива формула. We calculated the output signal of stochastic resonator by Runge-Kutta method, and by Volterra series. The calculation results are given in this figure. Volterra series is drawn by solid line, Runge-Kutta method is drawn by dotted line. Result from this figure show us that the numerical calculation by the Runge-Kutta method has a transient having duration of about 2 signal period. Further, the output signal calculation results obtained by the both methods are coincident. Совпадает. Так, next, Gaussian noise input. The leading term, значит, let's consider the input signal, which in zero means stationary Gaussian process with two-side power spectrum. The leading terms for the second moment of output signal are given in table. Это уже using the Volterra transfer function, we determine two-sided power spectrum of the output signal. The leading terms in the series for two-sided power spectrum are shown in table. What power spectra of output signal is shown on slide. Using these formulas, we construct a graph of the output signal power spectral density and compare it with the numerical calculation by Runge-Kutta method. Dotted line is the Runge-Kutta method, a solid line is the Volterra series. The graphs are similar, you can see. The output,
Not like before.
Да, не подгоняла, как получилось. Вот. The output signal power spectral density of stochastic nonlinear filter decrease with the frequency increasing, which is a characteristic for the nonlinear systems. Next, let's consider the sine wave plus noise input. It is possible to study the influence of the power spectral density noise, sine wave amplitude and system parameter of the output signal. Spike due to sine wave shown on the slide. This and this. Many formulas. Non-linear system. Leading terms of the output power spectrum. The output's power spectral density dependence on the frequency is shown on this slide. The dependence have a spike at 1 since f equal 4, the value of spectral power density almost will equal to 0. It is known that the model of rectangular pools is the basic in theories of information encoding. We will consider a case of so-called passive powers. Passive powers. Through that is not essentially when zero is provided by zero voltage. Consider a pool sequence as a useful input signal. Numerical solution of the stochastic resonance equation illustrated effective standard out of pulse signal from signal high intensive noise. значит, signal noise mixture black, high, output signal red. The signal to noise ratio becomes much higher as the output of the stochastic resonant filter than its input. We use the concept of squareness coefficient for the assessment for the pulse shape distortion. The squareness coefficient is defined as duration at the given level at the level of 0.7 of the maximum value. In practice, the condition level is selected equal to one of values 0.1, 0.01, 0.001. It is obvious that for the ideal rectangle pulse, squareness coefficient equal 1. Let's compare the quality of the signal standing out with the stochastic resonance usage by linear filter usage. Butterworth H's order filter was chosen as the linear selection system. The Butterworth filter provides a maximally flat response. Butterworth filter also sets the signal shape and increases steepness of the characteristics in the bandwidth. In the case of filter order increase. Result of numerical calculation are given in this figure. The quality of standing out characterized by squareness coefficient is also higher in case of stochastic resonator. Red point is a stochastic resonator, red point stochastic resonator, black point Butterworth filter. But Butterworth filter is linear filter. On this slide, the output signal to noise ratio dependence is shown. If the filter produces output in such a way that it maximizes the ratio of the output peak power to mean noise power in its frequency responses, then that filter is called matched filter. Matched filter used in radar. This is important criterion which is considered while designing by radar receiver. As you can see, the statistic resonance output signal to noise ratio is larger than matched filter output signal to noise ratio. Stochastic resonance matched filter. I cannot write formula matches filter. Currently, in radar information transmission, it carried out with radio signal image, where various types of modulation and manipulation of signal are used. Frequency modulated signals are widely used in radar, radio navigation, communication system, etc. The use of complex signal in radar provides a higher resolution in range and speed and can significantly increase the information content of radio system. The most commonly used linear frequency modulated signal and phasor modulated signal are the easiest to form and the process would provide the required qualitative parameter of the radar. The main advantages, long range and probability of detection, are combined with the high detection by range, reliability of detection on complex target and selection, high reliability of target classification by reflected signal, protection from the narrowband interference. Linear and frequency modulated signal. A feature of radio pulse with linear frequency modulated signal is the change in time of the instantaneous frequency and according to the linear law. You can see formula, you can see graphic, linear frequency modulated. In this figure, an example of signal standing out with LFM using as the effect is given. You clearly see the signal amplification and noise reduced at the input. You can see input signal mix signal and Gaussian noise black line and output signal red line. You can see dispersion decrease. Next, amplitude spectrum of the linear frequency modulated signal, blue line, and without noise, and the output signal, black line. You can see in this case the signal is amplified. Therefore, power gain is greater than 1. On this figure you can see the signal to noise ratio, output is gain greater, stochastic resonance is gain greater than the meshed filter output SNR. Значит, red line stochastic resonator output NSNR of the stochastic resonator. Black line is output meshed filter. Русский согласованный называется по-другому как-то.
Coordinated? Correlated.
Correlated.
I don't understand.
Correlated.
Согласованный.
Да, нет, matched, по-английски matched.
Matched.
По-английски matched, да. По-русски согласованно. Так, next type of signal, phase coda manipulated signal. The main difference between phasor coda manipulated signals, radio impulse, and regular radio pulse is that their high frequency filling initial phase change at certain time point for the certain amount. Those signals provide increased noise immunity and stealth effect. The mathematical model and the graph of the PSM signal are shown on this slide. Mathematical model signal. PSM signal on this slide. PSM signal standing out with stochastic resonant effects usage is shown. Black line is the input signal, red line is the output signal. Green is the harmonic signal. You can see that output noise dispersion is less than input one. Amplitude spectra. In this slide, the signal is amplified, therefore the power gain is greater than 1. The output SNR dependent on the noise dispersion is shown on this slide. Red line shows us the stochastic resonance dependence, black line is show matches the filter dependence. The stochastic resonator signal to noise ratio is greater than matched filter for all noise dispersion value. Local maximum in consider on 0.5. For the stochastic resonator. Conclusion, the stochastic resonator is good. Thank you for your attention.
Okay, thank you. If some questions, I will try to translate. It's different stuff. So many parameters to follow, to control.
I have a question. Are these results theoretical or you made some experiments?
Переведете? Я поняла. Ну, у меня есть схема, но мне некому ее спаять. У меня есть схема. Да. Все уже many years cannot find anything who do this scheme. Схема, имам схема.
It should be implemented in practice.
But
Did you try to find overlating on the Bulgarian?
Да. No, I read about experimental. People do scheme, read. But any device that have stochastic resonance effect. For example, как триггер Шмидта, как сказать по-английски? Триггер Шмидта. Да. Триггер Шмидта и туннельные диоды. Триггер Шмидта.
Триггер
это по-английски также.
Также триггер Шмидта, да. И диод. Туннельный диод, я не знаю, тоже, наверное, так же по-английски. Да. Но интересно, что мы даже слышим, когда шум небольшой есть, лучше слышим. Такой fundamental.
Yeah, so it's clear that this should be important problem forever. So many signals in the air, so you always have problem with them to make them free from noise, or enough free.
Это было, ну, я не знаю, как переводите. Сначала было очень странно. Я когда в Хайпер выступала, профессора говорили, такого не может быть. О чем она говорит? Физики ошиблись. Такого не бывает.
When she started to present such kind of results in Kharkov, and the colleagues said, no, this is impossible to happen.
Военная академия говорит, что она говорит? Я говорю, физики открыли, такого не может быть. Мы всю жизнь боремся с шумом, а тут шум помогает.
Yes.
Stanisław Horizon had some interesting concepts for potential denoising by adding noise of certain qualities, comparing the images, and several noise addition steps and so on and so forth.
Я поняла noise, а где применять не поняла.
У нас коллега, который работает что-то так, делает denoising.
Ну вот это тоже denoising.
Нет, сначала какой-то искусственный шум, и потом делает denoising, если я понял.
Да. Но это только фотоизображение.
Понятно. Я преподавала как digital imaging в том году. Digital imaging. Да, и видим мы тоже лучше, когда чуть-чуть шум присутствует.
Okay. No more comments.
Thank you.
Okay, by the way, all talks are recorded, I think.
And it is streamed.
Yeah, streamed, but they will be available as a record.
Yes,
tomorrow. Yeah. Okay, well, I mean, in the future. Yeah. Okay, so let us thank again. This was the last talk in this session and for today. And the next step, maybe Billy will say.
Those who are going to the restaurant should be at 6:30 in front of the institute. 6:30.
Which restaurant?